Welcome to the Late Lab, it's lovely to have you here. Before we settle in, let me ask you something gentle. Where in the world are you watching from tonight? Maybe you're tucked away in bed, listening with the lights low. Maybe you're on a quiet evening walk or curled up somewhere soft while the rest of the day finally loosens its grip. Wherever you happen to be, I hope you feel calm, comfortable, and ready to let your thoughts wander slowly. If you enjoy these quiet journeys through science, a like and subscribe is a lovely way to help this small, sleepy corner of the internet keep drifting along. And if you're already subscribed, thank you, truly. Your support makes these long, strange little voyages possible. Now, tonight's subject may be slightly dangerous for sleep because quantum physics has a habit of opening tiny doors in the mind and then refusing to close them properly. But if it keeps you awake for a little while, at least you'll leave with a clearer sense of why light can behave like both a wave and a particle, why uncertainty is built into nature, and why the smallest pieces of reality seem to follow rules that are both beautifully precise and deeply peculiar. So let's begin, gently. What is quantum physics? And why does the universe become so strange when you look closely enough? The world around you seems reassuringly solid. A cup rests on a table. A door stays where it is. Light pours softly through a window. Your body has weight. The floor has firmness. And if something rolls off the edge of a desk, it falls downward in a way that feels almost too familiar to notice. This is the world of ordinary experience. The world where things have places, shapes, speeds, and directions. It is the world your senses evolved to understand, because it is the world that mattered most for survival. Very few ancestors needed to know whether an electron could behave like a wave. They mostly needed to know whether the rustling in the bushes was dinner, danger, or just the wind showing off. For most of human history, nature appeared to behave in a mostly continuous and predictable way. Push something gently, and it moves gently. Heat something, and it warms. Throw a stone, and it follows a path. The great power of classical physics was that it took these familiar patterns and turned them into an astonishingly successful description of the universe. Isaac Newton showed that the same principles could describe falling apples and orbiting planets. His laws of motion and universal gravitation gave science a way to understand movement with extraordinary clarity. A cannonball, a moon, a pendulum, and a planet could all be treated as parts of one grand mechanical story. Then James Clerk Maxwell brought light, electricity, and magnetism into a single elegant framework. Maxwell's electromagnetic theory showed that light itself is a wave of electric and magnetic fields moving through space. It explained radio waves, visible light, and many behaviors of electricity and magnetism with remarkable power. Later, Albert Einstein reshaped classical ideas again with relativity, showing that space and time are not fixed stages, but woven together into space-time. He revealed that motion, gravity, light, and time were stranger than Newton had imagined, yet still described by laws that were clear, continuous, and deeply ordered. For large objects, these older frameworks still work beautifully. They are not wrong in the everyday sense. They are so reliable that engineers still use them to build bridges, guide aircraft, send spacecraft across the solar system, and predict the motion of ordinary objects with great accuracy. Classical physics is like a very good map of a familiar landscape. It shows the roads, rivers, hills, and towns clearly enough for almost every normal journey. But if that map is carried down into the world of atoms, it begins to blur. Quantum physics is the scientific description of matter, energy, light, and interactions at extremely small scales. It is the physics of atoms, electrons, photons, atomic nuclei, molecules, and the quantum fields that underlie particles. At these scales, nature does not behave like a tiny version of the everyday world. An electron is not just a miniature planet orbiting a miniature sun. A photon is not simply a little glowing pellet of light. An atom is not a microscopic solar system with neat tracks and tidy paths. Those images can be useful for a moment, but only as stepping stones. If held too tightly, they become misleading. The strange thing is not that quantum physics is chaotic, it is almost the opposite. Quantum physics is one of the most precisely tested and mathematically successful areas of modern science. It helps explain why atoms are stable, why stars shine, why chemicals bond, why metals conduct electricity, why magnets work, why lasers produce such pure light, and why modern electronics are possible. The phone, computer, or screen nearby is not merely using electricity in some vague general way. Its inner workings depend on the quantum behavior of electrons inside solid materials. The modern world runs partly on tiny rules that do not feel modern at all. They feel ancient, hidden, and quietly peculiar. At the scale of quantum physics, certainty softens into probability. This does not mean scientists simply shrug and guess. Quantum probability is not laziness wearing a lab coat. It is a precise and measurable feature of how small systems behave. Instead of always saying exactly where a particle is and exactly where it is going, quantum theory often gives a set of possible outcomes and the likelihood of each one. When measurements are repeated many times, those probabilities match experiments with remarkable accuracy. This is where everyday intuition begins to lose its footing. In ordinary life, an object seems to have a definite place whether anyone looks at it or not. A rolling ball does not appear to explore several possible paths before politely choosing one when observed. But quantum systems are described differently. A particle can behave in ways that resemble a spread-out wave, producing patterns of interference that no ordinary tiny ball could create. Light can behave like a wave as it spreads, bends, and interferes, yet it can also exchange energy in individual packets called photons. Matter itself, including electrons, can show wave-like behavior under the right conditions. This does not mean reality is imaginary, or that the universe is making things up casually as it goes along. Quantum physics is not a permission slip for any mystical claim that happens to sound mysterious in low lighting. It is a disciplined scientific theory built from experiments, predictions, mathematics, and repeated tests. Its strangeness comes from the fact that it works so well while resisting the simple pictures the human mind prefers. And perhaps that is the most important first step. The strange world of quantum physics is not hidden because it is distant. It is hidden because it is small, subtle, and usually averaged out by the larger world your senses can handle. It is inside the colours you see, because colour depends on how atoms and molecules absorb and emit light. It is inside sunlight, because nuclear processes and photons are part of the story of how stars shine. It is inside chemistry, because chemical bonds depend on electron behaviour. It is inside magnetism, electronics, materials, and life itself. The familiar world has not vanished. The table is still solid. The cup still rests. The falling object still falls. But beneath that calm surface is a deeper layer of nature, where particles are not quite like particles, waves are not quite like waves, and reality seems to hold several possibilities in quiet balance until interaction gives one of them a definite shape. The ordinary world is still here, steady and comforting. Quantum physics simply reveals that beneath it, something far stranger has been holding it up all along. By the late 19th century, physics had the quiet confidence of a grand old house, whose walls seemed perfectly straight, whose roof did not leak, and whose owner had perhaps become a little too pleased with the wallpaper. The universe appeared difficult, certainly, but not fundamentally mysterious in the way it would soon become. Many scientists believed the deepest rules were mostly in place. There were still measurements to improve, details to polish, and awkward corners to sweep, but the basic architecture looked strong. Newtonian mechanics described the motion of ordinary matter with astonishing success. Isaac Newton's laws could explain falling objects, swinging pendulums, cannonballs, tides, planets, and comets. The same mathematical principles that worked on Earth also worked in the heavens, which was a breathtaking idea. The moon was not held up by some special celestial rule. It was falling around Earth according to the same gravity that made an apple drop from a tree. This was one of the great unifications in science. The everyday and the cosmic brought under the same set of laws. Then came James Clerk Maxwell, whose electromagnetic theory joined electricity, magnetism, and light into one magnificent framework. Maxwell showed that electric and magnetic fields could travel together as waves, and that visible light was only one form of electromagnetic radiation. Radio waves, infrared light, visible colour, ultraviolet light, and other forms of radiation all belong to the same broad family. This was not just a useful theory. It was elegant in a way that made the universe seem almost polite, as though nature had written its rules with excellent handwriting. So by the end of the 1800s, classical physics seemed powerful enough to describe almost everything. Matter moved according to Newton. Light travelled as electromagnetic waves according to Maxwell. Heat and energy were described through thermodynamics and statistical mechanics. If nature still had secrets, many physicists expected them to be small secrets, the scientific equivalent of finding a missing teaspoon rather than discovering a trapdoor beneath the kitchen. But there was a problem glowing quietly in the corner. It began with something very ordinary. Heated objects. Warm a piece of metal enough, and it begins to glow red. Heat it further, and the glow shifts toward orange, yellow, and eventually white. This is not limited to metal. Hot objects emit radiation, and the pattern of that radiation depends on temperature. A cool object gives off mostly infrared radiation, which human eyes cannot see. A hotter object emits more visible light. Stars shine with colours linked to their surface temperatures. A red star is cooler than a blue-white star, though still not exactly chilly in the usual blanket and slippers sense. Physicists studied this problem using the idea of a black body. A black body is an idealized object that absorbs all radiation falling on it and emits radiation in a pattern determined only by its temperature. Real objects are not perfect black bodies, but the idea is extremely useful. Scientists built experimental cavities that acted very close to black bodies, allowing them to measure the radiation pattern with increasing precision. The measurements were clear. For any given temperature, the emitted radiation formed a smooth curve. There was a peak, where most energy was emitted, and then the intensity dropped away at both lower and higher frequencies. Classical physics could explain part of this pattern, but not all of it. At low frequencies, the predictions worked reasonably well. At high frequencies, especially in the ultraviolet range, classical theory went badly wrong. According to the classical prediction, a hot object should emit more and more energy at higher and higher frequencies. The amount of energy should climb without limit. In other words, the theory suggested that heated objects should pour out an impossible flood of high-frequency radiation. This failure became known as the ultraviolet catastrophe. It's a wonderfully dramatic name for a physics problem, as though someone had dropped a teacup and accidentally endangered the cosmos. The catastrophe was not that objects actually behaved this way. They did not. The catastrophe was that classical physics predicted something absurd. The old theory was trying to make the universe glow with impossible energy, and the universe, quite sensibly, declined. This was where Max Planck entered the story. In 1900, Planck was studying blackbody radiation and trying to find a formula that matched the observed curve. His solution was cautious, mathematical, and at first not meant as a grand philosophical revolution. Planck proposed that the energy exchange between matter and radiation could not vary in any amount whatsoever. Instead, it came in small, discrete packets. This was the beginning of the quantum idea. The word quantum means a discrete amount, a small measured portion. Rather than imagining energy as something that could be divided and exchanged with perfect smoothness, Planck treated it as arriving or departing in tiny steps. The size of each step depended on the frequency of the radiation. Higher frequency radiation came in larger packets of energy. Lower frequency radiation came in smaller packets. This idea allowed Planck to produce a formula that matched the black-body radiation. Experiments beautifully. The impossible ultraviolet flood disappeared. The curve behaved as the measurements said it should. The theory no longer demanded that hot objects radiate infinite energy at high frequencies. Nature, it seemed, had placed a kind of small-scale graininess into the exchange of energy. At first, this may have looked like a clever mathematical trick. Planck himself did not immediately treat it as a complete overthrow of classical physics. That is part of what makes the story so interesting. Quantum physics did not arrive with thunder, dramatic music, and someone kicking open a laboratory door. It began as a practical fix to a stubborn problem involving the glow of heated objects. But the fix was too good to remain small. If energy really came in discrete packets, then one of the basic assumptions of classical physics had cracked. Energy was not always exchanged as a smooth, continuous flow. At the smallest scales, it could behave as though nature counted in tiny portions. That idea sounds modest until it is allowed to spread. If energy is quantized in one situation, where else might the universe refuse to be smooth? This was the first deep crack in the classical picture. The old physics still worked beautifully across much of ordinary life. Bridges did not need quantum theory to stand. Planets did not need it to orbit in ways that could be calculated with great accuracy. But inside the glow of heated matter, something new had appeared. A small discontinuity, a measured step, a quiet refusal by nature to be infinitely divisible in the way classical intuition expected. From that point onward, physics could no longer remain entirely smooth and certain. The door had opened onto a stranger reality, where energy did not always pour like water, but sometimes arrived like individual drops. Light had already enjoyed a long and rather impressive career as a wave before quantum physics came along and made things awkward. By the late 19th century, James Clerk Maxwell's electromagnetic theory had given light a beautiful explanation. Light was understood as a travelling wave made from linked electric and magnetic fields, moving through space at an enormous speed. This picture was powerful, elegant, and successful. It explained reflection, refraction, interference, diffraction, polarization, and the way light could spread, bend, and overlap. For a while, light seemed to have confessed its identity quite clearly. It was a wave. Case closed. Nature, unfortunately for tidy-minded humans, had not finished giving evidence. The wave picture of light was not merely a guess. It had deep experimental support. When light passes through narrow openings, it can spread out. When two light waves overlap, they can reinforce each other or cancel each other, producing patterns of brightness and darkness. This behavior is hard to explain if light is imagined only as tiny particles flying in straight lines. Waves, however, do this naturally. Water waves do it. Sound waves do it. Light appeared to do it too, though without needing air or water to travel through. Maxwell's theory was so successful that it became one of the great pillars of classical physics. And then came the photoelectric effect. The photoelectric effect occurs when light shines onto certain metal surfaces and causes electrons to be released. At first, this might not sound especially strange. Light carries energy, electrons sit in metal, and if enough energy arrives, perhaps some electrons get knocked loose. That part seems reasonable. The trouble was in the details, and physics often becomes most interesting when the details refuse to behave. Classical wave theory suggested that the energy delivered by light should depend mainly on its intensity. A brighter light should carry more energy, so it seemed natural to expect that a very bright red light might eventually shake electrons free from a metal surface, given enough time. The wave could steadily deliver energy, like water filling a bucket. If the bucket needed more, just wait a little longer. Very polite, very classical. But experiments showed something different. Below a certain frequency, light would not release electrons at all, no matter how bright it was. A very intense beam of low-frequency light could shine on the metal, and still the electrons would remain in place. Meanwhile, a faint beam of higher frequency light could release electrons almost immediately. The brightness affected how many electrons were released, but the frequency determined whether each electron received enough energy to escape. This was deeply uncomfortable for classical wave theory. If light were only a smooth wave, energy should be spread through the wave and delivered gradually. Increasing the intensity should eventually do the job. But nature seemed to be saying that the colour, or more precisely the frequency, mattered in a sharper and more fundamental way. It was not enough for the light to be bright. Each individual interaction had to carry enough energy. In 1905, Albert Einstein proposed a bold explanation. Building on Max Planck's earlier work on black-body radiation, Einstein suggested that light itself could be treated as arriving in individual packets of energy. These packets were later called photons. Each photon carried an amount of energy determined by the frequency of the light. Higher frequency light, such as blue or ultraviolet light, came in more energetic photons. Lower frequency light, such as red or infrared light, came in less energetic photons. This separated two ideas that everyday language often blends together. The energy of each photon depends on frequency. The brightness of the light depends mainly on how many photons are arriving. So a bright red light can contain many photons, but if each photon lacks enough energy to free an electron from the metal, no electron escapes. A faint violet or ultraviolet light may contain fewer photons, but if each photon has enough energy, electrons can be released. A useful way to picture this is to imagine trying to open a little locked gate. 10 soft taps may not open it if each tap is too weak. One firm push might. Brightness gives more taps. Frequency gives stronger taps. The electron does not slowly collect a little energy from a broad, smooth wave until it has enough. In the photoelectric effect, it interacts with light in a way that makes sense if energy comes in packets. The universe, once again, appeared to be counting. Einstein's explanation was radical because it seemed to bring back a particle-like aspect of light, just when wave theory had appeared so triumphant. But this did not mean Maxwell was simply wrong. Light still behaves like a wave in many situations. It still interferes, diffracts, and spreads. But when light exchanges energy with matter, it can behave as though that energy arrives in individual portions. Light had not chosen one simple identity. It had become something more subtle. Robert Millikan later performed extremely careful experiments on the photoelectric effect. Interestingly, Millikan originally hoped to test Einstein's idea with great precision, not necessarily to celebrate it. Yet his measurements supported Einstein's prediction. The results confirmed that the energy of emitted electrons depended on the frequency of the incoming light in the way Einstein's photon idea required. This was one of those wonderful moments in science where careful measurement quietly overrules personal preference. The universe does not mind whether an idea feels comfortable. It only seems to care whether the numbers come out right. Einstein received the Nobel Prize in Physics for his explanation of the photoelectric effect, not for relativity, which is a small historical twist that often surprises people. Relativity may have become more famous in popular imagination, but the photon idea helped open the quantum door even wider. Light, once the great success story of classical wave theory, had revealed a second face. This is wave-particle duality. Light can travel, spread, and interfere like a wave, yet it can exchange energy like a collection of particles. It is not simply a wave pretending to be a particle, or a particle occasionally doing a little wave impression for attention. It is a quantum object, and wave and particle are older words being stretched to describe something deeper than either image alone. This strange behaviour is not locked away in old laboratory equipment. It sits quietly inside modern technology. Solar panels rely on photons transferring energy to electrons in materials, helping generate electric current from sunlight. Digital cameras detect photons when light strikes tiny sensors, turning individual quantum events into images. Light sensors, automatic doors, fibre optic communication, and many electronic devices depend on the interaction between photons and matter. So light refused to remain simple. It kept its wave-like grace, but gained a particle-like precision. It could ripple across space and still arrive in packets. It could make interference patterns and still knock electrons loose one interaction at a time. In doing so, light became one of the first clear signs that the quantum world would not fit neatly inside the old categories. The universe was not abandoning order. It was revealing a stranger kind of order, one measured not in smooth certainty, but in tiny packets of possibility. The atom is one of those ideas that sounds simple until it is looked at too closely. For a long time, it was imagined as the smallest possible piece of matter, the final grain beyond which nothing could be divided. The word itself comes from an ancient Greek idea meaning uncuttable, a tiny unit that could not be sliced into anything smaller. It was a beautiful thought, and in a way, a very reasonable one. If the world is made of things, perhaps there must be some smallest thing underneath it all, a final brick in the wall of reality. But nature has a habit of making the final brick contain a basement, a staircase, and a few unexpected cupboards. By the 19th century, the atomic idea had become far more than philosophy. Chemists had found that substances combined in fixed proportions, which made much more sense if matter was built from atoms of different kinds. John Dalton helped turn atoms into part of modern chemical theory, treating them as real units that could explain why elements formed compounds in predictable ways. Atoms were no longer just an ancient speculation. They were becoming a scientific model tied to measurement, experiment, and the behaviour of matter. Still, for much of that time, atoms were often imagined as small solid objects. They were the tiny beads of reality, different from one another perhaps, but not necessarily filled with moving inner parts. Then, near the end of the 19th century, that tidy picture began to break apart. J. Thomson discovered the electron in 1897 while studying cathode rays, streams of particles produced in glass tubes under low pressure. Thomson showed that these rays were made of negatively charged particles much smaller than atoms. This was a profound discovery because it meant atoms could not be the final indivisible pieces of matter. Something smaller existed inside them. The supposedly uncuttable atom had been cut open. Thomson proposed a model in which electrons were embedded inside a spread-out positive charge, a picture often nicknamed the plum pudding model. It was not correct in the end, but it was an important step. It showed that the atom had structure, it had ingredients. It was no longer a smooth little bead, but a system with charged parts arranged inside it. The atom had become a place where deeper physics could happen. Then Ernest Rutherford changed the picture again. In the early 20th century, Rutherford and his colleagues Hans Geiger and Ernest Marsden carried out the famous gold foil experiment. They fired alpha particles at an extremely thin sheet of gold and watched how the particles scattered. If Thomson's model were right, most alpha particles should have passed through with only slight deflections, because the positive charge would have been spread out softly through the atom. Most of the alpha particles did pass through, but a tiny fraction bounced away at sharp angles and some came almost straight back. Rutherford later compared it to firing a shell at tissue paper and having it rebound. That image is dramatic, but it captures the surprise. Something inside the atom was small, dense, and strongly positive. The atom was not a soft cloud of charge. It had a compact central nucleus. This discovery revealed one of the strangest facts about matter. Atoms are mostly empty space. Nearly all the mass of an atom is concentrated in a tiny nucleus, while the electrons occupy the much larger surrounding region. If an atom were enlarged to the size of a cathedral, the nucleus would be like a speck somewhere near the centre, while the electron region would stretch far outward. The exact comparison depends on the atom, but the lesson is clear. Solid matter is not solid in the way it appears. It is structured emptiness held together by forces and quantum rules. Rutherford's nuclear atom was a triumph, but it created a serious problem. In his model, negatively charged electrons moved around a positively charged nucleus. The attraction between opposite charges helped explain why electrons remained associated with the atom. But according to classical electromagnetism, moving charged particles should radiate energy. An electron orbiting the nucleus should lose energy continuously, spiral inward, and collapse into the nucleus very quickly. In other words, classical physics seemed to predict that atoms should not be stable. And this was awkward, because atoms were plainly doing a rather good job of existing. Tables, clouds, trees, teacups, stars, and slightly overconfident physics textbooks were all made of atoms that had not collapsed. Something essential was missing. In 1913, Niels Bohr proposed a new atomic model that used quantum ideas to explain atomic stability. Bohr suggested that electrons could occupy only certain allowed energy levels around the nucleus. They could not simply spiral inward through every possible energy value. Instead, electrons could remain in stable states, and they could jump between these states by absorbing or emitting definite amounts of energy. This was a bold move. Bohr's model did not treat the atom as a fully classical system. It introduced quantized electron energy levels, meaning the energies available to electrons came in discrete steps rather than a smooth continuum. This helped explain why atoms did not collapse. Electrons in allowed states did not radiate energy continuously in the way classical theory expected. They could emit or absorb light only when moving between specific energy levels. The model was especially successful for hydrogen, the simplest atom, with one electron around one proton. Hydrogen produces a set of distinct coloured lines when its light is split into a spectrum. These spectral lines had been measured long before the full quantum explanation was understood, but Bohr's model gave them a physical meaning. Each line corresponded to an electron changing energy by a specific amount and emitting or absorbing light of a specific frequency. Atomic spectra are like fingerprints of elements. When gases are heated or excited, they do not emit every colour smoothly. They produce particular lines depending on the allowed energy levels of their atoms. Hydrogen has its pattern, sodium has its pattern, neon has its pattern, which is why neon signs glow with such recognizable colour. Astronomers use these spectral fingerprints to identify elements in distant stars and galaxies. Light crossing space carries the quantum signatures of atoms across enormous distances, like tiny messages written into colour. Bohr's model was not the final picture of the atom. Later quantum mechanics replaced neat circular orbits with orbitals, probability clouds, wave functions, and a deeper mathematical description of electron behavior. Electrons are not little planets going around the nucleus on fixed tracks. The atom is stranger and subtler than that. But Bohr's model was historically crucial. It showed that atoms could not be understood using only smooth classical rules. Stability, light, and spectral lines all pointed toward discreteness. The atom had become a central stage for quantum physics, revealing that matter itself was built not from tiny solid beads, but from structured systems governed by allowed states, measured energy changes, and rules that classical intuition could not supply. The atom, once imagined as the simplest possible thing, had become one of nature's first great quantum riddles. By this point, light had already refused to stay in one tidy category. It could spread and interfere like a wave, yet exchange energy in packets like a particle. That was strange enough on its own. But quantum physics was not finished rearranging the furniture. The next step was even more unsettling, because the wave-like behavior did not belong only to light. Matter itself, the apparently solid stuff of the world, began to show wave-like properties too. This idea came from Louis de Broglie, a French physicist who proposed in 1924 that if light could behave both like a wave and like a particle, perhaps particles of matter could do something similar. Electrons, protons, atoms, and other bits of matter might not be only little objects moving along definite paths. They might also have an associated wavelength. This was a bold suggestion, because it took the strange dual nature of light and extended it into the material world. It was as though nature had whispered, "Oh, you thought only light was being difficult? How charming!" In everyday life this sounds almost impossible. A stone does not behave like a wave when it is thrown. A chair does not diffract around a doorway. A sleepy cat does not spread out across the room as a probability pattern, at least not unless it has discovered a very comfortable sofa. Ordinary objects seem solid and localized. They have definite positions. They move in familiar ways. But quantum wave behavior becomes noticeable only when dealing with very small particles, where the relevant wavelengths are large enough compared with the systems being studied. An electron can behave like a wave, but not because it is a tiny ripple of water or a little vibration travelling through air. The wave associated with an electron is not an ordinary material wave. It is connected to the electron's quantum state, the mathematical description that tells us what outcomes are possible and how likely they are. This quantum state can spread out, overlap, and interfere with itself in ways that affect what is later measured. The electron is not simply a miniature ball hiding inside a wave. It is a quantum object, and the old words particle and wave are both imperfect attempts to describe what it does. The evidence for matter waves came not just from clever reasoning, but from experiment. In the 1920s, Clinton Davison and Lester Germer studied electrons scattering from a crystal of nickel. They found that the electrons did not scatter in the way ordinary little pellets would. Instead, the pattern looked like diffraction, the behavior expected from waves interacting with a regular structure. The electrons were producing a wave-like pattern. Diffraction is easiest to imagine with ordinary waves. When water waves pass through a narrow opening, they spread out. When waves pass around an obstacle or through multiple openings, they can overlap. In some places, the wave crests reinforce one another, making a stronger effect. In other places, crest meets trough, and the waves partly cancel. This produces patterns that reveal the wave nature of what is passing through. Something similar happens with electrons, though the wave is not a sloshing substance. When electrons encounter the orderly arrangement of atoms in a crystal, their quantum states interact with that structure. The resulting pattern depends on the wavelength associated with the electrons. Davison and Germer's experiments showed that electrons could diffract in a way that matched de Broglie's proposal. Matter, at least at small scales, really did have wave-like behavior. This discovery deepened the mystery of the atom. In earlier atomic models, electrons had been pictured rather like tiny planets orbiting a nucleus. But if electrons have wave properties, that picture becomes much less reliable. Instead of imagining electrons as little beads on neat tracks, quantum physics describes them through states, patterns, and probabilities. In atoms, electron behavior has more in common with standing waves than with planets circling a star. Only certain wave patterns can fit around the nucleus in stable ways, which helps explain why electron energy levels are discrete. This also helps explain why quantum physics feels so strange. It does not merely add new facts to the old picture, it changes the kind of picture that can be drawn. In classical physics, an object normally has a path. It moves from one place to another through a sequence of definite positions. In quantum physics, an electron can be described by a state that spreads through space, and its later measurement is shaped by the entire pattern of that state. The mathematics works beautifully, but the mental image becomes slippery. The universe is not being unclear. It is simply not behaving like a scaled-down version of a billiard table. Matter waves are not only a philosophical curiosity, they also became practical. The electron microscope uses the wave nature of electrons to see structures far smaller than visible light can easily resolve. Ordinary light microscopes are limited by the wavelengths of visible light. Details much smaller than those wavelengths become difficult to distinguish. Electrons can be given much shorter wavelengths, allowing electron microscopes to reveal tiny structures in cells, materials, viruses, crystals, and nanotechnology. In other words, one of the strangest ideas in physics became a tool for looking more closely at the world. This is one of the quiet patterns of quantum physics. An idea begins as a puzzle that seems to disturb the foundations of reality, and later it becomes part of the equipment used in laboratories, hospitals, and technology. Matter behaving like a wave sounds dreamlike at first, almost too delicate to belong to real science. Yet electron diffraction is measurable. Electron microscopes are real. The wave nature of matter is built into the modern understanding of atoms, solids, chemistry, and materials. The deeper lesson is that quantum objects are not simply miniature versions of familiar things. An electron is not just a very small grain of dust. A photon is not just a tiny bead of light. At the smallest scales, nature uses rules that do not fit neatly into the categories human beings develop from watching stones, water, fire, and falling fruit. Sometimes matter behaves in ways associated with particles. Sometimes it behaves in ways associated with waves. And beneath those two older images is something more fundamental. The quantum state, spreading, interfering, and shaping what can be known. Matter, which seems so firm in ordinary life, turns out to have a hidden softness at its deepest level. Not softness in the sense of weakness, but in the sense of possibility. The solid world is built from entities whose behavior cannot be fully captured by solid images. Beneath every surface, every metal, every mineral, every living cell, and every quiet hand resting on a table, matter carries the memory of waves. Few experiments in science are as simple to describe and as difficult to fully absorb as the double-slit experiment. It begins with an almost childlike setup. A source sends something toward a barrier. The barrier has two narrow openings. Beyond it is a screen that records where the thing lands. That is all. No thunder, no cosmic machinery, no dramatic portal humming in a basement laboratory. Just two slits, a screen, and a question so deep It quietly unsettles the idea of what reality is doing when no one is measuring it. The roots of the experiment go back to Thomas Young in the early 19th century. Young used light passing through two openings to show that light behaves like a wave. If light were made only of simple particles travelling through one slit or the other, one might expect two bright patches on the screen, matching the two openings. But that is not what appears. Instead, light creates an interference pattern, a sequence of bright and dark bands. The bright bands appear where waves reinforce one another. The dark bands appear where waves cancel. This made excellent sense for waves because waves spread out, overlap and interfere. It was one of the great reasons light came to be understood as wave-like long before quantum physics arrived to make the situation more peculiar. The strange part begins when the same basic experiment is performed with quantum objects such as electrons. Electrons are usually described as particles. They have charge. They can be detected in individual spots. When an electron hits a screen, it does not smear across the whole surface like a mist. It appears as a single localized event, a tiny mark, a definite arrival. That seems particle-like. But when many electrons are sent through a double-slit apparatus, the pattern that slowly builds up is not simply two piles behind the two slits. It is an interference pattern. At first, one might think the electrons are bumping into one another somehow, like a crowd of tiny unruly travellers jostling their way through two doorways. So the experiment can be slowed down. Electrons can be sent one at a time, with enough space between them that each electron seems to be travelling alone. One electron leaves the source. One electron reaches the screen. A single spot appears. Then another electron. Another spot. At first, the dots look random, but as more and more electrons arrive, the pattern slowly emerges. The individual arrivals gather into bands of high and low probability, the signature of interference. This is where ordinary imagination begins to complain politely. If each electron arrives as a single spot, why does the long-term pattern look like a wave has passed through both slits? What exactly is interfering? It cannot simply be one electron colliding with another, because the electrons can be sent through one at a time. It cannot be explained by saying each electron is just a little ball going through, one slit in the ordinary way, because ordinary little balls would not gradually build up an interference pattern. The electron is behaving as though its quantum state passes through the arrangement in a wave-like way, while each final detection still appears as a single event. Later versions of this experiment have been performed not only with electrons, but with photons, neutrons, atoms, and even larger molecules under carefully controlled laboratory conditions. The details become technically demanding, because larger objects interact more easily with their environment, and that interaction tends to destroy visible interference. But the broad lesson remains. Quantum behavior is not just a quirk of light. It is a feature of physical reality at small scales, and sometimes at scales larger than early physicists might have expected. The double-slit experiment becomes even more revealing when an attempt is made to find out which slit the quantum object passes through. If a detector is placed so that the path can be known, the interference pattern disappears. The result on the screen changes. Instead of bands produced by interference, the pattern becomes more like what would be expected from particles passing through one opening or the other. The act of obtaining which path information changes the experimental situation. This point is often misunderstood. The experiment does not show that human consciousness magically creates reality. It does not mean the universe waits for a person to look at it with sufficiently dramatic eyebrows. In physics, measurement is not simply conscious awareness. It is an interaction that links the quantum system to some wider physical system in a way that records information. A detector, a screen, a surrounding environment, or another particle can all be part of the measurement process. The important point is that quantum information cannot always be gathered passively. To learn which path was taken, the system must be physically interacted with, and that interaction changes what kind of pattern can appear. This is the heart of the puzzle. Asking which path did it take, and observing an interference pattern are not just two different pieces of information that can be collected at the same time with better equipment. In quantum physics, the experimental arrangement matters. Some arrangements reveal wave-like behavior, others reveal particle-like behavior. The same quantum system can display different aspects depending on how it is measured. Niels Bohr called this idea complementarity. It means that quantum objects can require mutually exclusive experimental descriptions to reveal their full behavior. A photon or electron may show wave-like interference in one arrangement and particle-like detection in another. These descriptions are not simply mistakes. They are complementary ways of describing a reality that does not fit into one everyday image. Nature is not switching costumes for fun, though at times it does seem to have a flair for theatre. Rather, human categories such as wave and particle are limited tools being applied to something more fundamental. The double slit experiment matters because it strips the quantum mystery down to its cleanest form. Nothing enormous is required. No black holes, no beginning of the universe, no exotic machinery beyond careful experimental control, just a source, two openings, and a screen. Yet from this quiet arrangement comes a deep lesson. Reality behaves with reliable mathematical precision, but not with the simple visual clarity intuition expects. The interference pattern can be predicted. The probabilities can be calculated, the results can be repeated. Quantum physics is not chaos. It is not vagueness. It is not a scientific shrug. It is a theory of extraordinary discipline, describing a world where possibilities evolve according to strict rules and definite outcomes appear through interaction. The strangeness lies in the fact that between preparation and measurement, nature does not seem to follow the ordinary story of a tiny object travelling along one clear path. So the double slit experiment becomes a doorway. On one side is the familiar world, where objects appear to go through one opening or another, where looking simply reveals what was already there, and where reality seems to have a neat set of answers waiting in place. On the other side is the quantum world, where what can be known depends on how nature is questioned, where particles can behave like waves, and where the act of measurement is not just a glance, but part of the physical story. The double slit experiment leaves behind a quiet but stubborn question. If a quantum object does not simply follow one definite visible path in the ordinary way, then how does physics describe what it is doing before it is measured? The answer is one of the central ideas of quantum mechanics, the wave function. The wave function is the mathematical description used to represent the possible states of a quantum system. It does not usually describe a tiny object moving along a neat little road, the way a map might show a car travelling from one town to another. Instead, it describes a spread of possibilities. For an electron, a photon, an atom, or another quantum system, the wave function contains information about what outcomes may be found if a measurement is made. It is less like a photograph of a particle, and more like a carefully structured cloud of potential answers. This is already a strange shift. In everyday life, probability usually means incomplete knowledge. If a coin is flipped and hidden under a hand, the coin is already heads or tails. The uncertainty belongs to the person who has not looked yet. If a person says there is a 50-50 chance, they usually mean they do not know the answer, not that the coin is somehow waiting between possibilities in a deep physical sense. Ordinary probability often reflects ignorance about details that already exist. Quantum probability seems to go further than that. In quantum mechanics, the wave function does not merely hide a simple little classical story underneath. at least not in the standard interpretation. It gives the possible outcomes and their probabilities, and experiments suggest that these probabilities are built into the behavior of quantum systems themselves. This does not mean nature is random in a careless or messy way. Quantum theory is highly ordered. The wave function changes according to precise rules, but the outcome of a single measurement is not usually predicted with certainty. What can be predicted is the pattern of results over many repeated measurements. Erwin Schrödinger gave this strange new physics one of its most important tools. In 1926, he introduced the Schrödinger equation, which describes how a quantum state changes over time. The equation does not say, in ordinary visual terms, the electron is here, travelling along this exact path at this exact speed. Instead, it describes the evolution of the wave function. It tells physics how the possibilities unfold. That may sound like a retreat from reality, but it was actually a great advance. Schrödinger's wave mechanics could explain atomic behaviour with remarkable success. It helped replace the earlier image of electrons circling the nucleus like tiny planets with a more accurate description based on quantum states. These states could account for the allowed energy levels in atoms, the shapes of orbitals, and the patterns of light atoms emit and absorb. The atom became less like a miniature clockwork machine and more like a structure of permitted possibilities. But what exactly did the wave function mean? This question led to Max Born's probabilistic interpretation. Born argued that the wave function should be used to calculate the likelihood of different measurement outcomes. The wave function itself was not simply the physical smear of a particle spread through space like butter on toast, although that image is oddly peaceful. Instead, its mathematical structure gave probabilities. From it, one could work out where an electron was likely to be detected, what energy might be measured, or how a system might respond in an experiment. The key connection between the wave function and real measurements became known as the Born rule. In simple terms, the Born rule tells physicists how to turn the wave function into probabilities for possible outcomes. It is one of the essential bridges between the abstract mathematics of quantum theory and the actual clicks, flashes, marks, and readings seen in laboratories. Without that bridge, the wave function would be a beautiful but unanchored object. With it, quantum mechanics becomes a theory that can be tested with astonishing accuracy. This is one of the most important things to understand about quantum probability. It does not make physics vague. It makes physics statistical in a precise way. A single event may not be predictable with certainty, but the long-term pattern can be predicted extremely well. In the double-slit experiment, nobody can say exactly where one electron will land. But after many electrons arrive, the interference pattern forms according to the probabilities described by the quantum state. The individual dots seem unpredictable. The whole pattern is deeply lawful. The same principle appears across modern physics. Atomic spectra, the specific colours absorbed and emitted by atoms, can be predicted using quantum mechanics with extraordinary reliability. Semiconductor behaviour, which makes modern electronics possible, depends on quantum states and probability distributions in solid materials. Laboratory measurements of magnetic moments, energy levels, and particle interactions have confirmed quantum predictions again and again. In some areas, quantum theory agrees with experiment to such fine precision that it feels less like a rough sketch and more like nature, allowing science to read from an extremely small rule book, though perhaps one printed in very unusual handwriting. Probability, then, is not a weakness in quantum physics. It is part of its structure. The theory does not always tell us what will happen in a single case, but it tells us what can happen, how likely each outcome is, and how those possibilities change over time. This is very different from classical physics, where the future state of a system could in principle be predicted exactly if every starting detail were known. In the classical dream, uncertainty mostly comes from not knowing enough. In quantum physics, uncertainty appears to sit closer to the foundation. That raises a deeper question. Is the universe fundamentally uncertain, with probability woven into its deepest workings? Or does quantum uncertainty reflect a limit in the way human beings describe and measure reality? Different interpretations of quantum mechanics answer this in different ways. Some treat the wave function as a complete description. Others imagine deeper hidden structures, branching realities, or relationships between systems. The experiments give clear predictions, but the meaning remains more delicate. What is certain is that quantum physics changed the role of probability in science. It moved probability from the edge of knowledge to the center of nature. Beneath the calm surface of ordinary reality, the world is not always described by definite paths waiting to be uncovered. It is described by possible outcomes, evolving states, and patterns that only become clear when many small events gather together. The universe may not be careless, but at its smallest scales, it does seem to speak in probabilities. There is a particular kind of uncertainty that belongs to ordinary life. You may be uncertain where you left your keys. You may be uncertain whether tomorrow will be rainy. You may be uncertain whether a cake is fully baked without poking it, although this method has caused many brave sponges to collapse in the line of duty. In these cases, uncertainty usually means missing information. The answer exists somewhere. You simply do not have it yet. Quantum uncertainty is different. Werner Heisenberg introduced the uncertainty principle in 1927, and it became one of the clearest signs that quantum physics was not just a new set of facts, but a new way of thinking about what can be known. The uncertainty principle says that certain pairs of properties cannot both be known with unlimited precision at the same time. The most famous pair is position and momentum. Position means where something is. Momentum means how much motion something has, connected to both mass and speed. A slow-moving heavy object can have a lot of momentum. A fast-moving light object can have momentum too. In simple terms, momentum describes the strength and direction of an object's motion. In classical physics, there is no deep problem in imagining an object with both a definite position and a definite momentum. A thrown stone has a location, a speed, and a direction. Even if measuring these perfectly is difficult, classical physics suggests that the exact values exist. If the instruments were good enough and the starting information complete enough, the object's motion could in principle be known precisely. Heisenberg's uncertainty principle says that quantum systems do not work that way. For a particle such as an electron, a more precise knowledge of position comes with a less precise knowledge of momentum, and a more precise knowledge of momentum comes with a less precise knowledge of position. This is not mainly because the measuring device is clumsy, or because a scientist has bumped the table, or because the electron is being shy. The uncertainty is built into the structure of quantum states themselves. A gentle way to understand this is through waves. A simple wave with a very clear wavelength spreads out over a large region. Because its wavelength is well defined, its momentum is also well defined in quantum terms. But its position is not sharp, because the wave is spread out. To make something more localized, more like a wave packet gathered into a smaller region, many different wave components must be combined. The position becomes more defined, but the range of possible momenta becomes broader. This is not just a problem of language. It is a real mathematical feature of waves, and quantum objects are described by wave functions. If the wave function is squeezed into a narrow region, its momentum becomes less sharply defined. If its momentum is made very precise, the wave function spreads out in position. The uncertainty principle is therefore not a poetic way of saying small things are confusing. It is a precise scientific limit rooted in the wave-like nature of quantum systems. This matters because it changes the meaning of measurement. In ordinary life, measurement is often imagined as a passive act. You look at a chair and discover where it is. You check a clock and discover the time. But in quantum physics, measurement is tied to the nature of the system being measured. There are limits to the kinds of information that can be combined into one complete picture. Nature does not always provide a hidden label with every property written on it in tiny neat handwriting, which is inconsiderate perhaps, but apparently quite fundamental. The uncertainty principle also helps explain why atoms are stable. In a simple classical picture, one might wonder why an electron does not simply fall into the positively charged atomic nucleus and sit there. But if an electron were confined to the tiny space of the nucleus, its position would become extremely well defined. The uncertainty principle says that this would make its momentum highly uncertain and, in effect, very large. The electron could not simply rest motionless inside that tiny region. Confinement and momentum are deeply linked. This is one reason electrons occupy the wider regions around nuclei rather than collapsing neatly into the center. The full explanation of atomic structure involves quantum mechanics, electron energy levels, wave functions, and the electromagnetic force, but the uncertainty principle is an essential part of the story. It helps show why matter has size, why atoms do not collapse, and why the apparently solid world can exist at all. Heisenberg's idea can feel unsettling because it places a boundary around knowledge, not around human patience, not around engineering skill, but around what certain quantum properties can jointly possess in a sharply defined way. It says that at the smallest scales, reality cannot always be described as if it were made of tiny objects carrying perfectly definite positions and motions at every moment. Yet this is not a failure of science. It is one of science's most remarkable achievements. The uncertainty principle does not make the universe less lawful. It reveals a deeper law. It shows that the quantum world is not merely hidden from sight, waiting for better microscopes to expose it in familiar terms. It follows rules that decide what can be sharp, what must remain spread out, and what nature allows to be knowable. A quantum system is rarely as simple as it first appears. Before it is measured, it may not be best described as having one ordinary definite state, in the way a coin hidden under a hand is already heads or tails. Instead, quantum mechanics often describes it as a combination of possible states. This is called superposition, and it is one of the central reasons quantum physics feels so different from the world of tables, chairs, teacups, and other reassuring objects that usually know how to behave themselves. Superposition means that a quantum system can be represented as a mixture of possibilities before a definite outcome is observed. This does not mean it is confused. It does not mean scientists are simply unsure in the everyday sense. It does not mean a particle is secretly doing everything imaginable, like a tiny overachiever with no respect for scheduling. It means the mathematical state of the system genuinely contains more than one possible outcome, and these possibilities can influence one another before measurement. Electron spin offers a useful example, as long as it is treated carefully. Spin is an intrinsic quantum property, not simply a little electron rotating like a planet or a toy top. When measured along a chosen direction, an electron spin can produce one of two possible outcomes. But before that measurement, the electron can be prepared in a superposition of those outcomes. Its quantum state is not merely hiding a simple answer waiting to be uncovered. The state itself is arranged so that both possibilities are part of the description until measurement selects a result. Photon polarization gives another gentle doorway into the idea. Light can be polarized, meaning its electromagnetic vibration has a particular orientation. A photon can be prepared in a superposition of polarization states, and this produces measurable effects when it passes through filters. The outcome is not just a matter of not knowing which polarization the photon already had in some simple classical way. The superposed state affects the probabilities and patterns seen in experiments. Atomic energy states also show how superposition works. An atom can be placed in a quantum state that is a combination of different energy levels. This is not a vague metaphor. It affects how the atom absorbs and emits light, how it evolves over time, and how it behaves in precision experiments. Atomic clocks, spectroscopy, and quantum information experiments all depend on the fact that these states can be prepared, manipulated, and measured with astonishing care. Paul Dirac played a major role in developing the formal language of quantum mechanics that made this abstract state-based view so powerful. Dirac's work helped express quantum systems not as little mechanical pictures, but as states in a mathematical structure where superpositions arise naturally. In this view, combining states is not an optional decorative feature, it is built into the framework. Quantum physics does not begin with a tiny object wearing a tiny label saying exactly what it is doing. It begins with a state, and that state can contain multiple possibilities at once. The most important thing is that superposition is measurable. It is not imagination. It is not a poetic way of saying nobody knows yet. Superposition produces real interference effects. In the double-slit experiment, for example, the wave-like quantum state associated with a particle can involve alternatives that interfere with each other. If those alternatives are preserved, an interference pattern appears over many trials. If information about the path is recorded, the interference disappears. The superposition has physical consequences, even if it does not fit neatly into everyday language. This is why Erwin Schrödinger introduced his famous cat thought experiment in 1935. The point was not to suggest that anyone should put an actual cat in a box with a quantum device, which most cats would probably consider poor hospitality. Schrödinger wanted to expose how strange it becomes when quantum superposition is imagined at the scale of ordinary objects. If a microscopic quantum event could determine whether a larger system develops one way or another, then where exactly does the quantum description stop and the definite everyday world begin? Schrödinger's cat is often described as both alive and dead before observation, but this can be misleading if taken too casually. The thought experiment was designed to highlight a problem, not to claim that household animals routinely exist in magical half-and-half conditions. It asks how the rules that work so well for atoms and particles connect to the solid, definite world of living creatures, furniture, and breakfast. In the ordinary world, large objects appear definite because they constantly interact with their surroundings. A cat, a chair, or a dust grain is never perfectly isolated. Air molecules, light, heat, and countless tiny interactions continually carry information into the environment. This process is called decoherence. Decoherence explains how quantum alternatives lose the ability to interfere with one another when a system becomes entangled with its environment. It helps explain why the large world looks classical, stable, and definite, even though it is built from quantum pieces. Superposition also lies at the heart of quantum computing, though it is often exaggerated. A quantum bit can be placed in a superposition of two basic states, and multiple quantum bits can be arranged so their possibilities interfere. The power of quantum computing does not come from simply trying every answer at once in a magical instant. It comes from carefully using superposition, entanglement, and interference so that wrong possibilities tend to cancel and useful outcomes become more likely. Superposition is therefore not a trick of language. It is a real feature of quantum states, tested in laboratories and used in modern technology. It shows that before measurement, nature may not always carry one simple classical answer. Sometimes it carries a structured set of possibilities, quietly balanced, until interaction draws one outcome into the open. At the heart of quantum physics is a deceptively simple question. How does a world of possibilities become a world of definite facts? A quantum system can be described by a wave function, spreading through possible states, carrying probabilities rather than one ordinary fixed outcome. Yet when an experiment is performed, the result is not usually a soft blur of many answers. A detector clicks in one place, a screen records one mark, an atom emits one photon, a measuring device gives one reading. The many possibilities seem to narrow into one experienced event. This is the measurement problem. Quantum theory is extremely good at predicting probabilities. It can say how likely different outcomes are, and those predictions have been confirmed again and again with astonishing precision. In the double-slit experiment, it cannot usually predict exactly where one electron will land, but it can predict the pattern that appears after many electrons are detected. In atomic physics, it can predict spectral lines, transition probabilities, and the behavior of electrons in ways that match laboratory results beautifully. Quantum mechanics is not wobbling around uncertainly with a clipboard. It is one of the most successful predictive frameworks in science. The difficulty is not that the theory fails to work. The difficulty is understanding what is happening when a spread-out quantum state becomes one definite outcome. Before measurement, the wave function may describe multiple possible results. After measurement, one result is found. But what counts as a measurement? Does the wave function physically collapse? Is collapse only a useful calculation? Does every possibility somehow continue in a larger structure of reality? Or is there a deeper process beneath the standard theory? These questions are not casual late-night puzzling, although they do fit suspiciously well with late-night puzzling. They sit near the foundations of modern physics. John von Neumann gave one of the early formal treatments of measurement in his work on the mathematical foundations of quantum mechanics. He described quantum systems using precise mathematical rules and examined how measurement could be represented within the theory. Von Neumann's work helped sharpen the issue. If quantum systems evolve smoothly according to the Schrödinger equation, then measurement appears to introduce something different, a sudden update from many possible outcomes to one observed result. That contrast became one of the central conceptual tensions in quantum mechanics. The Copenhagen interpretation, associated especially with Niels Bohr and Werner Heisenberg, offered a practical way to think about the problem. In this view, quantum mechanics is mainly a tool for predicting the outcomes of measurements. It does not necessarily try to describe what a particle is doing in ordinary visual terms between preparation and observation. Bohr emphasized the role of experimental arrangements and the limits of applying everyday concepts to quantum systems. The Copenhagen approach helped physicists use quantum mechanics effectively without demanding a familiar picture underneath every equation. This practical attitude was powerful, but not completely satisfying to everyone. It can feel as though the theory says, in effect, here is how to calculate what you will observe. Please stop asking what is really happening behind the curtain. For many working physicists, that is often enough because the calculations work. For others, the curtain remains extremely tempting. Human curiosity has never been very good at seeing a curtain and deciding to leave it alone. A major modern idea connected to measurement is decoherence. Dieter Zeh and Wojciech Zurek were important figures in developing and explaining this concept. Decoherence describes what happens when a quantum system interacts with its environment. A carefully isolated quantum system can maintain superpositions, allowing alternatives to interfere. But large objects are not isolated. They interact constantly with air molecules, photons, heat, surrounding materials, and measuring devices. These interactions spread information into the environment and cause different quantum alternatives to stop interfering with one another. Decoherence helps explain why the everyday world appears classical. A dust grain, a chair, or a cat is constantly entangled with its surroundings. Any delicate quantum interference between visibly different states becomes effectively lost into the environment almost instantly. This is why large objects do not normally appear in obvious superpositions. The world around you looks definite, stable, and reassuringly unquantum, because its quantum alternatives are continually being scrambled into the wider environment. But decoherence does not necessarily solve every philosophical part of the measurement problem. It explains why interference between alternatives disappears and why the classical world emerges so convincingly. It explains why quantum weirdness becomes hidden in large systems, yet it does not, by itself, fully answer why one particular outcome is experienced rather than another. It turns a visible superposition into an effectively classical mixture, but the question of definite outcome can still remain, depending on the interpretation being used. That is why several interpretations of quantum mechanics exist. The many-worlds interpretation, associated with Hugh Everett, suggests that the wave function never collapses. Instead, all possible outcomes continue in different branches of reality, with observers becoming part of those branches. Pilot wave theory, associated first with Louis de Broglie and later developed by David Bohm, proposes that particles have definite positions guided by a real wave-like structure. Objective collapse models, associated with Ghirardi, Rimini, and Weber, suggest that wave function collapse is a real physical process that happens under certain conditions, rather than merely an update in knowledge. Each approach tries to make sense of the same experimental facts. None changes the everyday success of quantum mechanics in ordinary calculations. The disagreement lies in what the mathematics means. Is the wave function a complete description of reality? Is it a tool for prediction? Is collapse real? Are hidden variables guiding particles beneath the surface? Are all possible outcomes physically realized? These are not questions born from failure, but from success so precise that it exposes how strange the underlying picture really is. The measurement problem is therefore not a sign that quantum physics is broken. It is a sign that quantum physics works better than human intuition knows how to picture. The theory gives reliable probabilities, experiments confirm them, technologies depend on them. Yet the transition from possibility to actuality remains one of the deepest interpretive puzzles in science. Somewhere between the quiet mathematics of the wave function and the definite click of a detector, the strange world of quantum physics becomes the familiar world of experience. And that crossing, calm as it may look in a laboratory, is still one of the most mysterious boundaries in modern thought. There are some barriers that feel absolute in ordinary life. A wall is a wall. A locked door remains inconveniently locked. A hill cannot be crossed without enough energy to climb over it. In classical physics, this is usually straightforward. If an object does not have enough energy to get past a barrier, it stays on its side. A ball rolling toward a hill will climb only as far as its energy allows. If it cannot reach the top, it rolls back down. The hill does not politely allow it through just because the ball is having a determined afternoon. Quantum tunneling changes that picture. Quantum tunneling is the ability of quantum systems to pass through energy barriers that would be impossible to cross in classical physics. This does not mean particles are cheating, vanishing, or slipping through secret holes in the universe. It means that at small scales, particles are described by quantum states with wave-like properties. A quantum state does not always stop sharply at the edge of a barrier. It can extend into the barrier, becoming smaller as it goes. If the barrier is thin enough, there can still be a small chance that the quantum system will be found on the other side. This is one of the clearest examples of why quantum objects are not just tiny versions of familiar objects. A classical ball either has enough energy to cross a hill, or it does not. A quantum particle has a probability, however small, of appearing beyond a barrier that classical physics would forbid. The probability depends on the height of the barrier, the thickness of the barrier, and the properties of the particle. For large everyday objects, that probability is so fantastically tiny that it can be ignored. A person is not going to tunnel through a bedroom wall by accident, which is comforting for both privacy and architecture. But for subatomic particles, tunneling can matter enormously. One of the first major explanations involving quantum tunneling came from George Gamow in the 1920s. Gamow used tunneling to explain alpha decay, a type of radioactive decay in which an atomic nucleus emits an alpha particle. An alpha particle is made of 2 protons and 2 neutrons, the same structure as the nucleus of a helium atom. Inside a radioactive nucleus, an alpha particle can be trapped by the forces around it. Classically, it may not have enough energy to escape the nuclear barrier, yet radioactive atoms do emit alpha particles. Quantum tunneling explains how this can happen. The alpha particle's quantum state can extend beyond the barrier holding it inside the nucleus. Most of the time it remains trapped, but occasionally the particle is found outside. Once it appears beyond the barrier, it can move away, and the nucleus is decayed. This helped make radioactive decay understandable in quantum terms. The nucleus was not simply breaking a classical rule, it was following a deeper quantum one. Tunneling also plays a role in the sun. The sun shines because nuclear fusion occurs in its core, where hydrogen nuclei, mostly protons, can combine through a chain of reactions that eventually produce helium and release energy. Protons repel one another because they both have positive electric charge. To fuse, they must get extremely close enough for the strong nuclear force to become important. The sun's core is hot and dense, but even there, many protons do not have enough classical energy to overcome the full electrical repulsion between them. Quantum tunneling helps. The wave-like nature of protons gives them a small chance of getting through the repulsive barrier and close enough for fusion to proceed. This does not mean tunneling alone makes fusion easy. The conditions inside the sun are still extreme, with temperatures of about 15 million degrees Celsius in the core and immense pressure from the weight of the overlying layers. But tunneling is part of the reason fusion can happen at the rate it does. Without it, the sun's behavior would be very different, and sleepy science videos would have a much shorter list of comforting celestial objects to discuss. Tunneling is not only important in stars and radioactive nuclei, it can also be used as a tool. The scanning tunneling microscope, developed by Gerd Binnig and Heinrich Rohrer in the early 1980s, uses quantum tunneling to image surfaces at atomic scales. A very sharp conducting tip is brought extremely close to a surface. When a voltage is applied, electrons can tunnel between the tip and the surface. The tunneling current is very sensitive to the distance between them. Even a tiny change in separation can produce a noticeable change in current. By carefully scanning the tip across the surface and measuring this current, scientists can build images of atoms on a material. This is astonishing when paused over quietly. A phenomenon that sounds like an abstract quantum loophole became a way to see the arrangement of matter at the scale of individual atoms. The invisible strangeness became a measuring instrument. Tunneling also appears in modern electronics. Tunnel diodes use tunneling to create unusual electrical behavior. Flash memory, used in many storage devices, relies on electrons tunneling through thin insulating layers under controlled conditions. As transistors and electronic components become smaller, tunneling becomes both useful and troublesome. When barriers inside devices become extremely thin, electrons may tunnel where engineers do not want them to go, creating leakage currents and design challenges. At very small scales, the quantum world is not a distant philosophical problem. It is an engineering concern that shows up uninvited, sometimes wearing a hard hat. This is part of what makes tunneling such a beautiful example of quantum physics. It sounds impossible if imagined with ordinary objects. It feels like a particle passing through a wall it has no right to cross. But the effect is real, measurable, and essential to many physical processes. It appears in radioactive decay, helps stars shine, allows atomic-scale microscopes to work, and shapes the limits of modern electronics. Quantum tunneling is strange, but it is not imaginary. It is not magic wearing a laboratory coat. It is what happens when matter is governed by wave functions, probabilities, and barriers that are not as absolute as classical intuition expects. The universe does not always require a particle to climb over the hill. Sometimes, at the smallest scales, there is a small but real chance that it will be found quietly on the other side. Some quantum properties have names that are slightly misleading, and spin may be the finest example. The word sounds familiar. A spinning top spins, a planet spins, a wheel spins. So when quantum physics says an electron has spin, it is tempting to imagine a tiny charge ball rotating very quickly in place, like a microscopic planet with unreasonable enthusiasm. But quantum spin is not quite that. Spin is an intrinsic property of particles. It belongs to particles such as electrons in the way electric charge or mass belongs to them. It is not simply ordinary rotation scaled down to an incredibly small size. An electron is not known to be a little solid sphere turning on an axis. In fact, treating it that way leads quickly into problems, because the surface of such a tiny spinning object would need to move in impossible ways. Spin is better understood as a built-in quantum property that affects how particles behave in magnetic fields, how they combine with other particles, and how matter itself is organized. One of the most famous demonstrations of spin-related quantum behavior came from Otto Stern and Walter Gerlach in the early 1920s. Their experiment sent a beam of silver atoms through a specially shaped magnetic field. If the magnetic properties of the atoms behaved in a purely classical way, the beam might have spread into a smooth smear, with atoms deflected by many different amounts. That would be the ordinary expectation if the atoms could point their tiny magnetic orientations in any direction. Instead, the beam split into distinct parts. This was startling. The silver atoms did not behave as though their magnetic properties could take any value in a smooth range. They behaved as though only certain outcomes were allowed. The Stern-Gerlach experiment revealed a kind of discreteness at the heart of quantum measurement. When the atoms passed through the magnetic field, their magnetic behavior produced separated results rather than a continuous blur. It was another sign that the quantum world prefers steps, options, and allowed states where classical intuition expects smooth variation. Spin is closely connected to magnetism. Electrons have electric charge, and they also have spin. Together, these properties give electrons a tiny magnetic character. Each electron behaves a little like a minuscule magnet, though again not in the simple sense of a tiny bar magnet spinning in space. In many materials, the magnetic effects of individual electrons cancel out because their spins are arranged in opposing ways. But in some materials, many electron spins can align, and their tiny magnetic contributions add together. When enough of these quantum properties cooperate, they can produce the large-scale magnetism of a familiar magnet. So the magnet on a fridge door holding up a shopping list or a slightly optimistic meal plan is not merely a chunk of metal doing something ordinary. Its behavior comes from quantum properties of electrons, arranged across enormous numbers of atoms. The large magnetism that seems so simple in everyday life grows from hidden quantum order. Spin also plays a central role in the structure of atoms, partly through the work of Wolfgang Pauli. Pauli introduced the exclusion principle, one of the most important rules in quantum physics. The Pauli exclusion principle says that electrons cannot all occupy the same quantum state within an atom. Each electron must have its own allowed arrangement of quantum properties. This includes properties such as energy, orbital state, and spin. This rule is one of the reasons the periodic table has its structure. Electrons fill available quantum states around atomic nuclei in an ordered way. Because they cannot all collapse into the same lower state, they arrange themselves into shells and patterns. These patterns shape how atoms bond, how elements react, and why oxygen behaves differently from carbon, sodium, or iron. Chemistry, in a very real sense, depends on the refusal of electrons to all crowd into the same quantum seat. Pauli's rule is like the strictest theatre usher in the universe, calmly insisting that everyone has an assigned place. The Pauli exclusion principle also helps explain why matter has the structure it does. Ordinary objects do not pass through one another, partly because the electrons in their atoms resist being forced into identical quantum states. Electromagnetic forces are part of the story, but Pauli exclusion gives matter a deep quantum stiffness. It helps explain why atoms take up space, why solids have volume, and why the chair beneath someone does not simply allow all the particles involved to merge into one compact arrangement. This principle matters even in extreme astrophysical objects. White dwarf stars, the dense remnants left behind by stars like the Sun, are supported against further collapse by electron degeneracy pressure, which arises from the Pauli exclusion principle. In neutron stars, neutron degeneracy pressure becomes important. These are vast cosmic examples of a rule first needed to understand tiny quantum states. The very small and the very large are quietly connected again. Spin-related physics is also useful in technology, science and medicine. Electron spin resonance uses the magnetic behavior of unpaired electrons to study materials, chemical environments, and biological molecules. Magnetic resonance imaging, widely used in medicine, relies on the magnetic properties of atomic nuclei, especially hydrogen nuclei in water and fat inside the body. The technique uses strong magnetic fields and radio waves to gather information that can be turned into detailed images. The full engineering is complex, but the foundation reaches back to quantum spin and magnetic behavior. This is one of the most useful lessons in quantum physics. Some of its ideas resist simple mental pictures, but they are not vague. Spin cannot be pictured as ordinary rotation without creating confusion, yet it can be measured. It affects beams of atoms in magnetic fields. It shapes magnetism. It helps build the periodic table. It supports matter. It appears in medical scanners and laboratory instruments. Quantum spin is real, even if it is not visually simple. It reminds us that nature is not required to provide properties that look like familiar household objects. At the smallest scales, particles carry hidden qualities that obey precise rules, produce measurable outcomes, and combine to shape the world of magnets, chemistry, stars, bodies, and solid ground. The picture may resist imagination, but the effects are everywhere. Some of the strangest ideas in quantum physics involve single particles behaving in ways that defy ordinary expectation. But entanglement is stranger still, because it is not only about what one particle does. It is about what happens when two or more quantum systems are described together as one shared state, even when they later move far apart. Quantum entanglement occurs when the properties of separate systems cannot be fully understood independently. The systems may be separated in space, but the quantum description still connects them. If one part of the entangled system is measured, the result is correlated with the result found in the other part. These correlations can be stronger than anything allowed by a simple, classical picture, where each object merely carries pre-written instructions from the beginning. In ordinary life, separateness feels straightforward. Two coins can be placed into two envelopes and carried to opposite sides of a city. If one envelope is opened and the coin inside is found to be heads, that does not magically affect the other coin. Perhaps the coins were arranged in advance, so that one was heads and one was tails. The discovery tells us something we did not know, but it does not seem to change anything far away. Classical common sense likes this picture very much. It is calm, tidy, and does not threaten to ruin anyone's evening. Quantum entanglement does not fit so comfortably into that model. In 1935, Albert Einstein, Boris Podolsky, and Nathan Rosen published an argument now known as the EPR argument. They were not trying to celebrate quantum weirdness. They were challenging whether quantum mechanics could be a complete description of reality. Their concern was that quantum theory seemed to imply very strong connections between distant systems. If measuring one system could immediately tell something about another faraway system, then perhaps quantum mechanics was missing some deeper information. Maybe the particles carried hidden properties all along, and quantum theory simply did not describe them. Einstein famously disliked the idea of what he called spooky action at a distance. His discomfort was not foolish stubbornness. It came from a serious commitment to locality, the principle that physical influences should not travel faster than light. Einstein's theory of relativity had made the speed of light a central limit in nature. So if quantum mechanics seemed to suggest an instant connection across distance, that was not a small concern. It was a deep challenge to how reality should be understood. The important clarification is that entanglement does not allow faster-than-light messaging. Even if two entangled particles show strong correlations when measured, one observer cannot use their measurement result to send a chosen message instantly to the other. The outcome of each individual measurement still appears locally random. Only when the two sets of results are later compared through ordinary communication do the correlations become clear. This is known as the no-signaling principle, and it keeps entanglement from turning into a cosmic text message service with very poor customer support. For many years, the debate seemed almost philosophical. Were the strange quantum correlations truly part of nature, or were they caused by hidden variables, unknown properties carried by particles before measurement? Then John Bell changed the situation. In the 1960s, Bell developed what became known as Bell's theorem. He showed that if the world obeyed certain simple assumptions about locality and pre-existing hidden variables, then experimental results would have to obey specific limits, now called Bell inequalities. This was a remarkable transformation. Bell turned a deep argument about the meaning of quantum mechanics into something experiments could test. If quantum mechanics was right, certain entangled systems should produce correlations stronger than local hidden variable theories allowed. If local hidden variables were right, the correlation should stay within Bell's limits. Reality could be asked, carefully and mathematically, which side it preferred. Experiments gradually answered. Alain Aspect and his colleagues performed important Bell test experiments in the early 1980s, using entangled photons, providing strong support for quantum predictions. Later experiments became more refined, closing loopholes that could otherwise leave room for alternative explanations. Groups connected to Delft University of Technology, the National Institute of Standards and Technology, and the University of Vienna carried out major loophole-reduced Bell tests in the 21st century. These experiments strengthened the conclusion that nature does not fit simple local hidden variable explanations. This does not mean every philosophical question has vanished. Quantum interpretations still differ over what entanglement means at the deepest level. But the experimental lesson is powerful. Entangled systems behave as though their shared quantum state is more fundamental than any simple story in which each particle carries a complete set of separate, pre-written properties. The world is not behaving like a pair of envelopes containing ordinary hidden coins. Entanglement is now also a practical resource. In quantum information science, entanglement plays a central role in quantum communication, quantum cryptography, and quantum computing. Quantum cryptography uses quantum principles to help reveal attempts at eavesdropping. Quantum communication explores ways of transmitting quantum states and distributing entanglement. Quantum computing uses entanglement, superposition, and interference as part of its power. Though current machines remain technically difficult and far from magical all-purpose problem solvers, it is worth keeping the balance clear. Entanglement does not prove mystical unity. It does not allow thoughts to travel instantly through space. It does not let information outrun light. But it does show that the separateness of the world is not as simple as everyday intuition suggests. At the quantum level, the properties of distant systems may belong to a shared description, not to each piece alone. That is what makes entanglement so profound. It does not merely say that small things are strange. It says that the idea of a thing being fully independent may itself have limits. Two quantum systems can become linked in such a way that the whole carries information the parts do not possess separately. Beneath the familiar world of isolated objects, quantum physics reveals a quieter structure, where distance remains real, light speed remains respected, and yet separateness is not always the final word. By now, the quantum world has already become strange enough. Light behaves like both wave and particle. Matter shows wave-like behavior. Electrons occupy states rather than neat little paths. Entangled systems refuse to be understood as fully separate pieces, but modern physics goes one layer deeper still. Beneath the particle picture, beneath the little points and flashes and detector clicks, there is a broader framework called quantum field theory. Quantum field theory is the modern way physicists describe particles and forces at the smallest known scales. In this view, particles are not usually treated as tiny solid beads moving through empty space. Instead, they are understood as excitations of fields that extend throughout space. A particle is something like a localized ripple in an underlying quantum field. An electron is an excitation of the electron field. A photon is an excitation of the electromagnetic field. Other particles arise from their own fields as well. This does not mean space is filled with ordinary material jelly, which is perhaps a relief. A quantum field is not a substance in the everyday sense. It is a physical and mathematical entity that assigns possible values to every point in space and time. Fields can carry energy, interact, fluctuate, and produce measurable effects. In quantum field theory, the deep furniture of reality is not made only of particles sitting in space, but of fields from which particle-like events can emerge. This deeper view became necessary because early quantum mechanics, powerful as it was, didn't fit naturally with special relativity. Albert Einstein's special relativity showed that the laws of physics must respect the speed of light and treat space and time as joined together. But early quantum mechanics was often built around particles moving more slowly and systems where particle number stayed fixed. At high energies, or when particles move close to the speed of light, this is not enough. Particles can be created and destroyed. Energy can become matter. Matter can become radiation. A deeper framework was needed. Paul Dirac helped open this door. In 1928, Dirac developed a relativistic equation for the electron. It combined quantum mechanics with special relativity in a new and powerful way. But the equation did something astonishing. It implied the existence of a particle like the electron, but with opposite electric charge. This was antimatter. A few years later, Carl Anderson discovered the positron, the electron's antimatter counterpart, in cosmic ray observations. Dirac's theory had pointed toward a hidden symmetry in nature, and experiment found it. This was a remarkable moment. The mathematics had not merely explained a known particle, it had predicted something new. Antimatter was not science fiction at the time, though it has since been adopted enthusiastically by science fiction, often with concerning explosions. It was a real feature of the universe, revealed by the attempt to make quantum theory and relativity work together. One of the most successful quantum field theories is quantum electrodynamics. Quantum electrodynamics describes how light and electrically charged particles interact. It is the quantum field theory of the electromagnetic force. Richard Feynman, Julian Schwinger, Shinichiro Tomonaga, and Freeman Dyson played major roles in developing it into a practical and extraordinarily precise theory. It explains processes involving electrons, photons, and electromagnetic interactions with astonishing accuracy. Quantum electrodynamics introduced ways of calculating particle interactions using diagrams, often associated with Feynman. These diagrams are helpful tools, but they can also be misunderstood. They sometimes include what are called virtual particles. It's important to be careful here. Virtual particles should not be imagined too literally as tiny objects popping in and out of empty space like fireflies having a nervous evening. They are features of mathematical calculations, internal parts of the method used to describe interactions between quantum fields. They are useful and meaningful within the theory, but they are not particles detected in the same way as ordinary electrons or photons. Quantum field theory eventually became the foundation of the Standard Model of particle physics. The Standard Model describes the known elementary particles and three of the four fundamental interactions: electromagnetism, the weak nuclear force, and the strong nuclear force. It does not include gravity in a complete quantum way, which remains one of the great unfinished problems in physics. But within its domain, the Standard Model has been astonishingly successful. Major research institutions have tested this framework again and again. The European Organisation for Nuclear Research, widely known as CERN, operates the Large Hadron Collider near Geneva. Fermilab in the United States has also played a major role in particle physics, including studies of quarks, neutrinos, and high-energy collisions. In these places, particles are accelerated to enormous energies and smashed together, allowing physicists to study the fields and interactions beneath ordinary matter. One of the most famous examples is the Higgs field. The Higgs field is a quantum field associated with the mechanism that gives certain elementary particles mass. Peter Higgs, François Englert, and Robert Brute were among the physicists who developed this idea in the 1960s. The Higgs boson is the particle associated with excitation of the Higgs field. In 2012, experiments at the Large Hadron Collider announced the discovery of a particle matching the expected Higgs boson. It was a profound confirmation that a field-filling space could have detectable consequences. The Higgs field is a useful reminder that fields are not just mathematical decoration. They shape what particles are able to do. They influence the properties of matter. They help determine why some particles have mass while photons do not. The idea is strange, but not vague. It is tested through collisions, detectors, patterns of decay, and careful statistical analysis by thousands of scientists. Quantum field theory expands the strange world of quantum physics from individual particles to the structure beneath particles. It suggests that what seems like a particle may be a ripple in something deeper. It shows that empty space is not merely a blank stage, but a place where fields exist, interact, and define the possibilities of matter and force. The universe is not just filled with objects, it is threaded with fields, and those fields form the hidden grammar from which particles, light, and interactions arise. Empty space sounds simple. It sounds like the easiest thing in the universe to describe. Remove the planets, remove the stars, remove the dust, remove the gas, remove every drifting atom and every faint photon of light, and surely what remains is nothing. A blank, a quiet absence, a place where physics can finally put its feet up and stop being difficult. But quantum physics is not especially fond of simple endings. In modern physics, empty space is not usually treated as absolute nothingness. Absolute nothingness would mean no matter, no energy, no space, no time, no fields, no laws, no possibilities, and no physical structure of any kind. That is more of a philosophical idea than a laboratory condition. The quantum vacuum is something different. It is the lowest energy state of quantum fields. It is what remains when a field has no ordinary particles present, but still exists as a field. It is empty of particles in the usual sense, but it is not empty of physical meaning. This distinction matters. In quantum field theory, fields are not optional decorations placed inside space. They are part of the deep structure used to describe particles and interactions. An electron is an excitation of the electron field. A photon is an excitation of the electromagnetic field. If those excitations are absent, the field is in its vacuum state. But the field itself has not disappeared. The stage has no actors visible, perhaps, but the stage is not the same as non-existence. It still has rules, structure, and measurable consequences. This is where the idea of vacuum fluctuations enters. Vacuum fluctuations are fluctuations in quantum fields, even when no ordinary particles are present. They should be described carefully. It is tempting to imagine empty space as a tiny sparkling soup of particles constantly popping into and out of existence like impatient fireflies. That image is memorable, but it can be misleading if taken too literally. Vacuum fluctuations are not usually ordinary particles briefly appearing as visible little objects before vanishing again in embarrassment. They are features of quantum fields and their lowest energy states, appearing in the mathematics and in measurable effects linked to field behavior. The reason these fluctuations are possible is tied to the uncertainty principle. Quantum systems cannot always have every property fixed with perfect sharpness. A field in its lowest energy state is not like a perfectly still classical object. It can have unavoidable fluctuations because the quantum rules do not allow all motion-like and field-like properties to be exactly zero in the simple classical sense. Even at minimum energy, there is still a kind of irreducible quantum restlessness. Not chaos, not magic. Just the quiet hum of a system that cannot be made perfectly still. This minimum energy is called zero-point energy. It is the lowest energy a quantum system can have. A simple classical oscillator, like an ideal weight on a spring, could in principle sit completely motionless at its lowest point with no energy of motion. But a quantum oscillator cannot be made perfectly motionless in that way. Its position and momentum cannot both be pinned down with unlimited precision, so it retains a minimum amount of energy. Quantum fields can be understood as having many oscillator-like modes, and their vacuum states carry this same general idea of irreducible minimum energy. One of the most famous measurable effects connected to the quantum vacuum is the Casimir effect, named after the Dutch physicist Hendrik Casimir. In 1948, Casimir predicted that two closely spaced conducting plates in a vacuum could experience a tiny attractive force because of the quantum behavior of the electromagnetic field between and outside the plates. The plates restrict which field modes can exist between them compared with the space outside. This difference leads to a measurable pressure pushing the plates together. The Casimir effect is delicate. It is not something noticed between ordinary dinner plates, which is fortunate because washing up does not need additional quantum complications. The effect becomes important only at extremely small separations, usually on the scale of nanometers to micrometers. Experiments have measured forces consistent with Casimir's prediction, showing that the quantum vacuum is not a purely abstract idea. Even when ordinary particles are absent, the behavior of fields can leave a detectable trace. This does not mean empty space is packed with usable infinite energy, or that the vacuum is a hidden cosmic battery waiting for someone to attach the right plug. That is a common exaggeration. Zero-point energy and vacuum fluctuations are real concepts within quantum theory, but extracting unlimited energy from the vacuum is not supported by established physics. The universe is strange, but it is not usually generous in exactly the way Internet inventions would prefer. Vacuum concepts also appear in particle physics and cosmology. In the Standard Model, fields have vacuum states, and the Higgs field is especially important because its non-zero value throughout space helps explain why certain elementary particles have mass. In cosmology, the vacuum becomes part of discussions about dark energy, the mysterious cause associated with the accelerated expansion of the universe. Observations show that cosmic expansion is speeding up, and dark energy is one way scientists describe the effect. But connecting this directly and cleanly to quantum vacuum energy remains one of the major unresolved problems in theoretical physics. This is an important place to be careful. Quantum field theory suggests that vacuum energy should exist, while cosmological observations suggest a very small but significant energy density associated with empty space. Yet the simplest theoretical estimates do not match the observed value in a straightforward way. The mismatch is enormous, and it remains one of the deepest puzzles in modern physics. So the quantum vacuum is real within established theory, and dark energy is supported by astronomical evidence, but the exact relationship between them is not fully understood. That kind of honesty is part of good science. Quantum physics does not prove that nothing is secretly everything in a mystical sense. It does not show that empty space contains wishes, thoughts, or hidden spiritual instructions written between atoms. What it does show is already strange enough. Empty space, as physics describes it, has fields. Those fields have vacuum states. Those vacuum states can have fluctuations, zero-point energy, and measurable effects. Absence in modern physics is not always simple. The quantum vacuum is one of the quietest ideas in science, but also one of the most unsettling. It suggests that even when every ordinary particle is removed, something physical remains, not matter, not light in the usual sense, not a substance that can be poured into a cup and served with biscuits, but a structured lower state of fields, governed by quantum rules, carrying possibilities that can shape experiments, and perhaps even touch the history of the universe. So empty space is not quite empty. It is not full in the ordinary sense, and it is not nothing in the absolute sense. It is a strange middle ground, silent, dark, nearly featureless to the eye, yet still described by fields that refuse to become perfectly blank. In the calmest emptiness physics can imagine, the quantum world is still there, quietly reminding reality that even absence has rules. Chemistry can look wonderfully tangible from the outside. A crystal has a shape. Water flows, wood burns, sugar dissolves, a leaf catches sunlight. A body breathes, repairs, grows, and quietly performs more chemical work in a single moment than any kitchen counter has ever seen, even on a very ambitious baking day. But beneath all these familiar transformations is a smaller and stranger foundation. Chemistry is deeply quantum. Atoms do not bond because they are tiny balls with little hooks. They do not share electrons in the way people share umbrellas or biscuits. Atoms bond because electrons are quantum objects, and their allowed states determine how matter can arrange itself. Electrons have energy levels. They have spin. They are described by wave functions and probability distributions. They obey the Pauli exclusion principle. When atoms approach one another, their electron states can combine, shift, overlap, and form new arrangements. These arrangements decide whether atoms will bond, how strongly they will bond, what shape a molecule will take, and how that molecule will interact with light, heat, water, metals, proteins, and everything else in the chemical world. The simple ball and stick picture of molecules is useful, especially for visualizing structure. It can show that water has one oxygen atom and two hydrogen atoms, or that carbon atoms can form long chains and rings. But it is not the deeper explanation. Real chemical bonding is described more accurately through electron configurations and molecular orbitals. Electron configurations describe how electrons occupy allowed quantum states in atoms. Molecular orbitals describe how electron states spread across a molecule rather than belonging only to one atom. In a molecule, electrons are not always neatly parked between two nuclei like tiny glue droplets. They can be distributed across regions of space, shaping the molecule's stability, geometry, and reactivity. Linus Pauling was one of the major figures in bringing quantum mechanics into chemistry. His work helped explain chemical bonding, molecular structure, electronegativity, and the nature of covalent bonds. Pauling showed that the strange mathematics of quantum physics could be used to understand the real shapes and behaviors of molecules. Chemistry, which might once have seemed like a catalogue of substances and reactions, became connected to a deeper theory of electron states and atomic structure. This quantum foundation is also why the periodic table has its pattern. The table is not just an elegant filing cabinet for elements, although it is certainly one of science's finest filing cabinets. Its rows and columns arise because electrons occupy energy levels and orbitals according to quantum rules. The Pauli exclusion principle, introduced by Wolfgang Pauli, says that electrons cannot all occupy the same quantum state within an atom. Because of this, electrons fill available states in an ordered way, creating shells and patterns that repeat as atomic number increases. Those repeated electron patterns produce the chemical families: reactive alkali metals, noble gases, halogens, and many others. So when sodium reacts strongly with chlorine, or oxygen supports combustion, or carbon forms the backbone of life's molecules, quantum physics is there beneath the chemistry. The visible reaction is the large-scale expression of electron behavior. Chemistry is quantum physics with enough atoms involved to become fragrant, colourful, useful, dangerous, delicious, or occasionally all of those in the wrong order. Life depends on this. Biological molecules are shaped by quantum chemistry. Proteins fold into specific structures because of interactions between atoms and electrons. DNA holds genetic information through molecular bonds, base pairing, and the geometry of large organic molecules. Enzymes speed up chemical reactions by arranging molecules in ways that lower energy barriers and guide electrons and atoms through reaction pathways. The full story of enzyme action belongs to chemistry and biology, but its deepest foundation is quantum. Bonds forming and breaking, electrons shifting, and atoms moving through allowed physical possibilities. Photosynthesis offers one of the most beautiful examples. In plants, algae, and some bacteria, molecules absorb photons of light and use that energy to help drive chemical processes. Chlorophyll and related pigments absorb specific colours because their electrons have particular quantum energy levels. When light is absorbed, energy moves through molecular systems and eventually helps convert carbon dioxide and water into energy-rich chemical forms. This is not mystical. It is not sunlight being turned into life by poetic intention. though poetry may politely stand nearby. It is quantum chemistry operating inside living cells, refined by evolution over immense spans of time. Vision also begins with quantum events. In the retina, molecules called retinal, bound within proteins known as opsins, absorb photons. When a photon is absorbed, the retinal molecule changes shape, triggering a chain of biological signals that the nervous system eventually interprets as sight. Every visible scene begins with countless tiny interactions between light and molecules. A sunset, a candle flame, a face, a page of writing, a blue sky at dusk, all of them begin as quantum exchanges before they become experience. There is also an active field called quantum biology, which studies cases where explicitly quantum effects may play important roles in living systems. One area involves energy transfer in photosynthetic complexes, where researchers investigate how quantum coherence might help energy move efficiently through molecular structures, at least for very short times and under specific conditions. Another area involves magnetoreception in birds, where some evidence suggests that quantum spin effects in light-sensitive proteins called cryptochromes may help certain animals sense Earth's magnetic field. These are fascinating areas of research, but they should be treated carefully. Quantum biology does not mean life is magic. It does not prove that consciousness is a quantum field, or that thoughts can alter reality, or that cells are secretly tiny mystical computers humming with cosmic wisdom. Living systems are physical systems. Since quantum physics underlies chemistry, and chemistry underlies biology, life necessarily depends on quantum rules. The question in quantum biology is more specific. Where do delicate quantum effects remain important in the warm, wet, noisy environment of living organisms? And where do ordinary biochemical descriptions work well enough? That distinction matters. The role of quantum, physics and chemical bonding, molecular structure, photosynthesis and vision is well established. More delicate claims about long-lasting quantum coherence in complex biological processes require careful evidence. The strange world of quantum physics is already essential to life without needing exaggeration. Reality is impressive enough without giving every molecule a tiny wizard hat. The body, the leaf, the cell, and the enzyme are not separate from the quantum world. They are built from it. Every breath depends on molecules shaped by electron states. Every muscle contraction depends on chemical energy released through molecular processes. Every thought depends on living tissue whose structure and function arise from chemistry, and that chemistry rests on quantum rules. The world of life feels warm, soft, and continuous, but underneath it are atoms, electrons, photons, bonds, orbitals, spins, and energy levels. Quantum physics is not confined to particle accelerators or cold laboratory chambers. It is inside the green of leaves, the chemistry of blood, the structure of proteins, the absorption of light in the eye, and the quiet architecture of DNA. Life does not escape the strange rules of the small, it grows from them. Quantum physics can sound as though it belongs only in remote laboratories, sealed behind thick doors, surrounded by complicated equipment, warning labels, and people calmly adjusting things that look expensive enough to make a person nervous. But the strange rules of the quantum world are not confined to particle accelerators or thought experiments. They are already woven into ordinary life. Much of modern technology works because matter, light, and electrons behave quantum mechanically. The device playing this video, the screen glowing in the dark, the camera that may have recorded the image, the internet signals carrying the data, and even the clock keeping everything synchronized all depend, in one way or another, on quantum physics. The modern world does not look especially quantum from the outside. It looks like glass, metal, plastic, wires, and screens. But beneath those familiar surfaces are energy levels, electron states, photons, semiconductors, magnetic effects, and carefully engineered materials whose behaviour cannot be fully explained by classical physics alone. One of the most important examples is the semiconductor. A semiconductor is a material whose ability to conduct electricity sits between that of a conductor and an insulator. Silicon is the most famous example. What makes semiconductors useful is not simply that electricity can pass through them, but that their electrical behaviour can be precisely controlled. That control depends on band structure, which is a quantum description of the allowed energy states available to electrons inside a solid. In an isolated atom, electrons occupy specific energy levels. In a solid, where enormous numbers of atoms sit close together, those levels broaden into bands. Some bands are filled with electrons, while others are available for electrons to move into. The gap between these bands helps determine whether a material behaves as an insulator, a conductor, or a semiconductor. By adding tiny amounts of selected impurities, a process called doping, engineers can change how many electrons or electron vacancies are available to move. This is the foundation of modern electronics. The transistor grew out of this quantum understanding of materials. John Bardeen, Walter Brattain, and William Shockley are associated with the invention of the transistor at Bell Labs in 1947. A transistor can act as a switch or amplifier, controlling the flow of electrical current. This sounds simple, but it became one of the most important inventions in technological history. Modern computer chips contain billions of transistors, each one helping process information through controlled electrical behavior in semiconducting materials. The transistor is not quantum because it looks mysterious. It is quantum because its function depends on electron energy bands, charge carriers, material interfaces, and the behavior of electrons in solids. Classical electricity alone cannot explain why silicon behaves the way it does, or why carefully engineered semiconductor structures can become the foundation of computing. Every tap on a screen, every saved file, every quiet loading bar pretending not to test your patience, depends on quantum rules working reliably, at enormous scale. Lasers are another everyday quantum technology. The word laser refers to light amplification by stimulated emission of radiation. Albert Einstein laid the theoretical foundation for stimulated emission in 1917. Stimulated emission occurs when an incoming photon encourages an excited atom or molecule to release another photon with the same energy, direction, and phase. When this process is arranged carefully inside a laser, it produces light that is highly coherent, meaning the photons are organized in a very orderly way. Theodore Maiman built the first working laser in 1960 using a ruby crystal. Since then, lasers have become astonishingly common. They appear in fiber optic communication, barcode scanners, surgical tools, manufacturing equipment, rangefinders, printers, scientific instruments, and the tiny optical systems used to read data. A laser beam may look like a clean line of light, but its existence depends on quantum transitions between energy levels. It is organized light produced by the rules of atoms and photons. Atomic clocks show quantum precision in another form. Isidore Rabi helped develop methods using atomic and molecular beams that eventually led toward extremely precise timekeeping. Atomic clocks use the fact that atoms can transition between specific energy states at extremely stable frequencies. Cesium atomic clocks, for example, are central to the definition of the second. The National Institute of Standards and Technology in the United States operates some of the world's most precise atomic clocks, contributing to global timing standards. This matters far beyond laboratories. Satellite navigation systems, telecommunications networks, financial systems, power grids, and internet infrastructure all depend on precise time. When a phone finds its location using satellite signals, timing errors of tiny fractions of a second can become large position errors. Atomic clocks allow technology to coordinate events with extraordinary accuracy. The steadiness of quantum transitions becomes the steadiness of modern timekeeping. Magnetic resonance imaging also depends on quantum behavior. In medical scanners, atomic nuclei, especially hydrogen nuclei in the body's water and fat, respond to strong magnetic fields and radio waves. Their magnetic properties are connected to quantum spin. By detecting how these nuclei respond, scanners can build detailed images of soft tissues inside the body. The resulting images may feel like ordinary hospital technology, but the underlying physics reaches down to the quantum properties of nuclei. Light-emitting diodes also rely on quantum processes. In an LED, electrons and electron vacancies recombine inside a semiconductor, releasing energy as photons. The color of the emitted light depends on the energy gap in the material. Solar cells work in a related quantum world, absorbing photons and using their energy to move electrons into states where electrical current can be generated. Charge-coupled devices, once widely used in digital cameras and astronomy, detect light by converting incoming photons into electronic signals. Computer chips, camera sensors, solar panels, medical scanners, lasers, and atomic clocks are all different expressions of the same deeper truth. The modern world is already quantum, not because it is glowing with strange symbols or behaving like a science fiction control room, but because small-scale rules quietly support ordinary tools. Quantum physics helps explain why materials conduct, why screens shine, why sensors detect, why clocks keep time, why images can be formed from light, and why information can move through global networks. This is perhaps one of the gentlest surprises in the whole story. The quantum world may feel distant, abstract, and difficult to picture, but it is not distant from daily life. It is inside the practical objects people use without thinking. It is in the circuits, clocks, lamps, cameras, scanners, and signals that surround modern existence. The strange rules beneath reality have become so reliable that they now help the ordinary world run quietly in the background. Quantum computing is one of those subjects that seems to arrive surrounded by fog machines, glowing headlines, and the faint sound of someone promising that all passwords, medicines, weather forecasts, and traffic jams will be solved by Tuesday. The real subject is quieter, more precise, and much more interesting. Quantum computing is not magic computing. It is an attempt to use the actual rules of quantum physics, including superposition, entanglement, and interference, to process information in ways that ordinary classical computers cannot easily copy. A classical computer stores and manipulates information using bits. A bit has one of two possible values, usually described as 0 or 1. These values can be represented by electrical signals, magnetic states, or other physical arrangements. Everything a classical computer does, from displaying an image to running a spreadsheet to making a loading bar pretend progress is happening, can be built from enormous numbers of these simple binary choices. A quantum computer uses quantum bits, usually called qubits. A qubit is a physical quantum system that can be prepared in a combination of two basic states. These basic states are often compared to the 0 and 1 of a classical bit. But the comparison has limits. A qubit can be placed in a superposition, meaning its quantum state includes both possibilities in a structured way before measurement. However, when a qubit is measured, the result is definite. The measurement gives one outcome or the other, according to the probabilities described by the quantum state. This is where the first common misunderstanding appears. A qubit is not simply both 0 and 1 in the everyday sense. like a coin somehow lying heads up and tails up at the same time on a table. Nor does a quantum computer automatically try every possible answer and then hand over the correct one with a small bow. If it were that simple, quantum computing would already have solved rather more problems, including the mystery of why printers choose moments of emotional importance to stop working. The power of quantum computing comes from controlling quantum states carefully, then using interference to shape the final probabilities. Quantum states can combine, overlap, and interfere, much like waves can reinforce or cancel one another. A good quantum algorithm is designed so that wrong or unhelpful possibilities tend to interfere destructively, reducing their chance of appearing in the final measurement, while useful possibilities interfere constructively, increasing their chance. The final answer still comes from measurement, but the path to that measurement uses quantum behavior in a way classical systems do not naturally reproduce. Richard Feynman was one of the key figures in making this idea feel necessary. In the early 1980s, Feynman pointed out that quantum systems are extremely difficult for classical computers to simulate efficiently. The reason is that the number of possible quantum states grows very rapidly as more particles are included. Even a modest quantum system can require an enormous amount of classical information to describe fully. Feynman suggested that perhaps the best way to simulate quantum physics would be with machines that are themselves quantum. David Deutsch then helped develop the idea of a universal quantum computer, showing that quantum computation could be treated as a general model of computation, not just as a special tool for one type of simulation. This moved the subject from a clever suggestion into a deeper theoretical framework. Quantum computers were not just unusual machines, they were a new way to think about information, physics, and computation together. One of the most famous breakthroughs came from Peter Shor in the 1990s. Shor's algorithm showed that a sufficiently powerful fault-tolerant quantum computer could factor large numbers much more efficiently than the best-known classical methods. Factoring means breaking a large number into the smaller numbers that multiply together to make it. This matters because some widely used cryptographic systems rely on factoring being extremely difficult for classical computers when the numbers are large enough. Shor's algorithm became famous because it showed a clear theoretical case where quantum computing could threaten an important classical security assumption. It did not mean every password suddenly became unsafe overnight. Real quantum computers capable of breaking modern encryption at large scale would need far more reliable qubits, better error correction, and much greater engineering maturity than current machines generally possess. Still, Shor's result was profound. It proved that quantum computers were not merely strange toys for physicists. In principle, they could change what kinds of calculations are practical. Love Grover found another important quantum algorithm. Grover's algorithm gives a speed-up for searching through an unsorted set of possibilities. It does not make search instant. It does not let a computer pull the answer from the cosmic filing cabinet without opening the drawers. But it does offer a genuine advantage. For certain kinds of search problems, a quantum computer can reduce the number of steps needed compared with a straightforward classical approach. This is a more modest advantage than Shor's algorithm, but it is still important because it shows another way quantum interference can be useful. Quantum computing may also be especially valuable for simulating quantum systems. This brings the idea back toward Feynman's original motivation. Chemistry, material science, superconductivity, and particle physics all involve quantum behavior that can be very hard to calculate exactly with classical computers. A mature quantum computer might help scientists study molecules, catalysts, materials, and reactions in ways that are currently impractical. This could matter for drug discovery, battery chemistry, fertilizers, clean energy materials, and many other fields. But the word might is important. The potential is real, but the road is difficult. The central challenge is that quantum states are delicate. Superposition and entanglement are powerful, but they are also easily disturbed by unwanted interaction with the environment. This problem is called decoherence. Heat, stray electromagnetic fields, vibrations, imperfect controls, and measurement-like interactions can all damage the quantum information before a calculation is complete. A quantum computer must protect its qubits long enough to perform useful operations, while also controlling them precisely enough to guide the computation. Errors are another major issue. Classical computers also have errors, but they can be managed very effectively using robust digital logic and error correction. Quantum error correction is more difficult because quantum information cannot simply be copied in the ordinary way. This is connected to the no-cloning theorem, which says an unknown quantum state cannot be perfectly copied. Instead, quantum error correction spreads information across entangled groups of physical qubits, so that errors can be detected and corrected without directly measuring and destroying the encoded information. This means that a truly powerful, fault-tolerant quantum computer may require many physical qubits to create one reliable logical qubit. The exact number depends on the hardware, error rates, architecture, and error correction method. But the general lesson is clear. Building a useful quantum computer is not just a matter of making more qubits. They must be high-quality qubits, controlled with extraordinary precision, connected in useful ways, and protected from noise. Many current machines are described as noisy intermediate-scale quantum devices. This phrase refers to quantum processors with enough qubits to be scientifically interesting, but not enough reliability or error correction to run the most transformative large-scale algorithms. These devices are valuable for research. They help scientists and engineers learn how to control quantum systems, test algorithms, improve hardware, and explore near-term applications. But they should not be mistaken for finished universal quantum machines ready to replace classical computers. Institutions and companies around the world are working on different approaches. IBM Quantum has developed superconducting quantum processors and cloud access to quantum systems. Google Quantum AI has also worked with superconducting qubits and demonstrated milestone experiments in quantum processing. IonQ uses trapped ions, where individual charged atoms are held and manipulated using electromagnetic fields and lasers. Rigetti Computing works with superconducting quantum hardware. Academic groups worldwide explore many other platforms, including neutral atoms, photons, silicon spin qubits, topological approaches, and hybrid systems. Each approach has strengths and weaknesses. Superconducting qubits can be fabricated using methods connected to existing electronics technology, but they require extremely low temperatures and careful control. Trapped ions can have excellent coherence and high-quality operations, but scaling them into very large systems is challenging. Photonic quantum computing uses particles of light, which are naturally good at traveling and communicating, but creating reliable interactions between photons is difficult. The field is active because no single path has clearly won, so quantum computing should be treated with both excitement and patience. It is not a guaranteed near-future miracle, and it is not an empty buzzword either. It is a serious scientific and engineering effort built on real quantum principles. It may become powerful for specific tasks, especially quantum simulation, cryptography-related calculations, optimization-related methods, and certain mathematical problems. It will not make classical computers obsolete for everyday work. No one needs a quantum computer to write an email, watch a video, or forget where a file was saved. The most honest picture is also the most interesting one. Quantum computing is the attempt to turn the strangeness of quantum physics into a controlled form of information processing. It takes superposition, entanglement and interference, not as mysteries to admire from a distance, but as tools to be engineered. The challenge is that these tools are delicate, demanding, and often deeply uncooperative. Yet if they can be controlled well enough, they may allow certain calculations that classical machines would struggle to perform. Quantum computing is not the universe handing humanity a magic shortcut. It is something subtler, a way of asking whether the strange rules beneath matter can be made to compute. And that question, even without the hype, is remarkable enough. Quantum physics often feels as though it belongs to the very small, electrons, photons, atoms, nuclei, and the hidden architecture of matter. Cosmology seems to belong to the very large, galaxies, clusters, black holes, cosmic expansion, and the enormous distances between stars. At first they feel like opposite ends of science, one peering inward and the other outward. But the universe is not divided so neatly. To understand the larger structures in existence, physics must look back to a time when the entire observable universe was once incredibly hot, dense, and compressed into a state where quantum effects mattered deeply. The early universe was not a quiet collection of galaxies drifting through darkness. Galaxies had not yet formed, stars had not yet switched on, atoms themselves did not exist in the familiar way. The universe was filled with an extremely hot mixture of particles, radiation, and fields, expanding and cooling as time moved forward. In those earliest moments, the boundary between particle physics and cosmology almost disappears. The story of the whole universe becomes a story of fields, quantum fluctuations, energy, and space-time itself. One of the most important ideas connecting quantum physics to cosmic structure is cosmic inflation. Cosmic inflation is the proposal that, very early in the universe's history, space expanded at an extraordinarily rapid rate for a brief period. Alan Guth was one of the first physicists to propose inflation in the early 1980s, and Andre Linde developed important versions of inflationary theory soon afterward. The exact details remain an active area of research, but the basic idea is powerful. A tiny early region of the universe could have expanded enormously, stretching space itself on a scale almost impossible to picture. Inflation was proposed partly to solve puzzles in cosmology. It helps explain why the universe looks so smooth and uniform on very large scales, even in regions that seem too far apart to have exchanged light or information in the ordinary way. It also helps explain why the geometry of the observable universe appears very close to flat. But one of its most fascinating consequences is that it may have stretched tiny quantum fluctuations into the seeds of cosmic structure. In quantum field theory, fields are not perfectly still, even in their lowest energy states. They have fluctuations. In the early universe, these tiny fluctuations could have created extremely small differences in density from place to place. During inflation, those fluctuations may have been stretched across enormous distances. After inflation ended, the universe continued expanding and cooling, and those slight density differences remained. Regions that were a little denser than average had slightly stronger gravity. Over immense spans of time, gravity amplified those small differences, pulling matter together into galaxies, galaxy clusters, and the great web-like structure seen across the cosmos today. This is one of the most astonishing ideas in modern science. The largest structures in the universe may have grown from tiny quantum variations in the earliest moments of cosmic history. The clusters of galaxies spread across hundreds of millions of light years may carry the faint memory of quantum behavior from when the universe was unimaginably young. The very small did not stay small. It was stretched into the architecture of the very large. Evidence for this story comes partly from the cosmic microwave background, the oldest light seen across the universe. The cosmic microwave background is radiation released when the universe cooled enough for electrons and atomic nuclei to combine into neutral atoms about 380,000 years after the hot Big Bang. Before that time, light scattered constantly from free electrons and could not travel freely across space. Once neutral atoms formed, light could stream through the universe. Today, that ancient light has been stretched by cosmic expansion into microwave radiation, forming a faint glow in every direction. Measurements of the cosmic microwave background reveal tiny temperature variations. These variations are extremely small, but they are not random noise. They are a map of early density differences, the seeds from which later cosmic structure grew. The Cosmic Background Explorer helped detect the overall spectrum of this ancient radiation and found its tiny fluctuations. The Wilkinson Microwave Anisotropy Probe mapped those fluctuations with greater precision. The Planck Space Telescope later measured the cosmic microwave background in even finer detail, giving scientists one of the most precise views of the early universe ever made. These observations support the idea that the universe began in an extremely smooth state, with small variations that later grew under gravity. Inflation remains a theoretical framework, with details still being tested and debated. But the broad connection between early fluctuations and later structure is central to modern cosmology. The Great Cosmic Web, with galaxies arranged along filaments and clusters, may be the grown-up version of subtle early unevenness. It is a little like seeing a vast forest and tracing it back to the faintest scattering of seeds, except the seeds were quantum fluctuations and the forest is made of galaxies. Nature does enjoy working at an unreasonable scale. Quantum physics also meets cosmology in one of the strangest places imaginable, the edge of a black hole. In classical general relativity, a black hole is a region where gravity is so strong that nothing, not even light, can escape from within the event horizon. But in the 1970s, Stephen Hawking applied quantum field theory to curved space-time near black hole horizons and found a remarkable result. Black holes should not be completely black. They should emit a faint form of radiation, now called Hawking radiation. The basic idea is that quantum fields near the event horizon behave differently because of the extreme gravitational setting. To a distant observer, the black hole can appear to emit particles and gradually lose energy. For large astrophysical black holes, Hawking radiation is incredibly faint, far colder than the cosmic microwave background, so it has not been directly observed from real black holes. But the theoretical result is deeply important because it links quantum theory, gravity, and thermodynamics. This connection leads to the black hole information problem. If a black hole forms from matter containing information about its quantum state, and then slowly evaporates through Hawking radiation, what happens to that information? Quantum mechanics suggests information should not be fundamentally destroyed. Classical black hole physics seems to hide it behind the horizon. Hawking radiation complicates the picture further. The problem sits at the meeting point of quantum theory, general relativity, and thermodynamics, and it remains one of the deepest unresolved puzzles in theoretical physics. The larger issue is quantum gravity. General relativity, Albert Einstein's theory of gravity, describes gravity not as an ordinary force in space, but as the curvature of space-time caused by mass and energy. It works beautifully for planets, stars, galaxies, gravitational waves, and the large-scale expansion of the universe. Quantum physics works beautifully for atoms, particles, fields, and the microscopic structure of matter. But when both are needed at once, such as inside black holes, or at the earliest moments of the universe, the two frameworks do not yet fit together completely. A complete theory of quantum gravity remains one of science's greatest open goals. It would need to explain how space-time and gravity behave according to quantum principles, without losing the successful predictions of general relativity or quantum field theory. No confirmed final theory exists yet. The universe, once again, is understood with extraordinary precision in many domains while still keeping one of its deepest foundations unresolved. Quantum physics began as a way to understand light, atoms, and matter, yet it reaches outward until it touches the shape of the cosmos itself. The largest structures in existence may carry the imprint of quantum fluctuations. Black holes may reveal quantum effects through their horizons. The earliest universe may require physics that has not yet been completed. The strange world of quantum physics is not only beneath reality. In a quiet and astonishing way, it may also be written across the sky. Quantum physics has a slightly unusual place in science. It is one of the most successful theories ever created, and also one of the most difficult to picture clearly. It predicts the behavior of atoms, electrons, photons, semiconductors, lasers, magnetic materials, particle interactions, and countless laboratory measurements with extraordinary accuracy. Quantum field theory, especially quantum electrodynamics, has matched some experimental results with a precision that is almost absurdly good, as though nature is letting scientists read the fine print, but only through a very strange pair of glasses. And yet, prediction is not the same as complete understanding. Quantum mechanics can tell us what probabilities to expect when a measurement is made. It can describe how a quantum state changes over time. It can explain atomic spectra, chemical bonds, tunneling, interference, entanglement, and the behavior of particles in fields. But it does not automatically settle every question about what the theory means. The mathematics works. The experiments agree. The technology functions. The phone does not pause to have an existential crisis before using semiconductor physics. But the conceptual picture behind the theory remains deeply debated. One of the great open questions is the measurement problem. Before measurement, a quantum system can be described by a wave function containing several possible outcomes. After measurement, one definite result is observed. A detector clicks, a screen records a mark. An atom is found in one state rather than another. Quantum theory gives the probabilities extremely well, but the transition from a spread-out quantum state to one experienced outcome remains conceptually difficult. Does the wave function physically collapse? Does collapse only represent an update in knowledge? Are all outcomes somehow real in a larger structure? Or is the usual theory incomplete in a deeper way? Different interpretations answer these questions differently. Copenhagen-style views, associated with Niels Bohr and Werner Heisenberg, focus on what can be predicted and measured, and are often practical rather than visually satisfying. The many worlds interpretation, associated with Hugh Everett, suggests that the wave function never collapses, and that different outcomes continue in branching parts of reality. Pilot wave theory, associated with Louis de Broglie and David Bohm, proposes that particles have definite positions guided by a real wave-like structure. Objective collapse models, associated with Girardi, Rimini, and Weber, suggest that collapse is a real physical process that happens under certain conditions. No single interpretation has been universally accepted. This is not because physicists are casually indecisive, like someone staring at a menu for 40 minutes and still ordering chips. It is because many interpretations reproduce the same observed results, while telling different stories about what is happening underneath. Experiments strongly constrain what can be true, especially through Bell tests and other quantum foundations work, but they do not yet force one universally agreed picture of what the wave function ultimately is. The wave function itself remains a central mystery. Is it a real physical thing? Is it a description of knowledge? Is it a tool for calculating probabilities? Is it relational, depending on how systems are connected to one another? Carlo Rovelli's relational quantum mechanics takes seriously the idea that the state of a system is not absolute, but defined relative to other systems. This does not mean reality is imaginary. It means the properties described by quantum physics may not exist in the same observer-independent way classical objects seem to possess them. It is a careful proposal, not a settled fact. Roger Penrose has explored speculative ideas connecting wave function, collapse, with gravity. In these proposals, gravity might play a role in turning quantum possibilities into definite outcomes. These ideas are interesting and have inspired debate, but they are not established physics in the same way as standard quantum mechanics or general relativity. They belong to the frontier, where a theory may be suggestive, mathematically motivated, or philosophically appealing, but still awaits decisive evidence. Science has room for speculation, but it has to keep its shoes on the ground even when its head is somewhere near a black hole. The deepest unfinished problem may be quantum gravity. General relativity, Albert Einstein's theory of gravity, describes gravity as the curvature of space-time caused by mass and energy. It works beautifully for planets, stars, galaxies, gravitational waves, black holes, and cosmic expansion. Quantum theory, by contrast, describes fields, particles, probabilities, superpositions, and interactions at small scales. Each framework is enormously successful in its own domain, but in places where both should matter, such as the centre of black holes or the earliest moments of the universe, the two theories do not yet form one complete picture. This is difficult because general relativity treats space-time as dynamic geometry, while quantum theory usually treats fields and particles as quantum states evolving within a background of space and time. If space-time itself must be quantum, then the stage is no longer separate from the actors. The geometry, the fields, the particles, and the probabilities may all need to be part of one deeper framework. That is an enormous challenge, and nature has not made the answer obvious. Subtle? Yes. Beautiful, perhaps. Convenient? Not especially. Candidate approaches exist. String theory, associated with many researchers including Edward Witten, proposes that fundamental objects may be tiny extended strings rather than point-like particles, and it naturally includes a quantum description of gravity in certain mathematical settings. Loop quantum gravity, associated with researchers including Lee Smolin and Carlo Rovelli, explores the possibility that space-time geometry itself has a quantum structure. Both approaches have produced important ideas, but neither has been confirmed as the final theory of quantum gravity. This is where scientific honesty becomes important. Not yet known is not a weakness. It is one of the strongest phrases in science when evidence is incomplete. It protects understanding from becoming performance. Quantum physics does not need every mystery solved in order to be real, useful, or astonishingly accurate. A map can be extraordinarily reliable while still leaving distant regions unfinished. That may be why quantum physics remains so strange. It is not strange because it fails. It is strange because it succeeds so well while refusing to become fully intuitive. It reveals a universe that can be measured with breathtaking precision, yet not always pictured in ordinary human terms. Beneath the familiar world is a theory that explains matter, light, chemistry, technology, and perhaps the seeds of cosmic structure, while still leaving open some of the deepest questions ever asked. Quantum physics is not the end of mystery. It is one of the clearest ways science has found to approach it. The strange world of quantum physics is not separate from reality. It is not hidden in some distant laboratory, far away from ordinary life, waiting behind glass walls and warning signs. It is woven into the behavior of light, matter, atoms, chemistry, technology, stars, empty space, and the quiet structure of the world itself. It is beneath the colour of a leaf, the glow of a screen, the warmth of sunlight, the bonding of molecules, the ticking of atomic clocks, and the deep processes that allow matter to exist in stable forms. What began with cracks in classical physics became one of the greatest changes in scientific thought. Max Planck's quantum idea showed that energy could come in discrete packets. Albert Einstein's photons revealed that light could exchange energy like particles while still behaving like a wave. Niels Bohr's atom showed that electrons occupied allowed energy levels rather than collapsing into the nucleus. Matter waves, the double slit experiment, probability, uncertainty, superposition, measurement, tunneling, spin and entanglement all pointed toward a reality that could not be squeezed into ordinary pictures. Then quantum fields carried the story deeper still, suggesting that particles are excitations of underlying fields spread through space. The quantum vacuum showed that even empty space is not a simple blank. Quantum technology revealed that these strange rules are not only theoretical, but practical, shaping semiconductors, lasers, solar cells, medical scanners, cameras and clocks. Cosmology carried the same ideas outward, linking tiny quantum fluctuations to the vast structure of galaxies and the unresolved mysteries of black holes and gravity. Quantum physics is strange not because it is loose, mystical, or imaginary, but because it is precise in ways that do not match everyday intuition. It has been confirmed across countless experiments and technologies, while still leaving deep questions about interpretation, measurement, quantum gravity, and the ultimate nature of reality. The ordinary world feels solid and familiar, because quantum behavior usually hides beneath larger patterns. But beneath every surface, every atom, and every quiet beam of light, nature is following rules stranger and more exact than the human mind first expected.